welcome to your YouTube Knowledge Academy. The meaning of this lecture is to discuss about the control system formulas in a very detailed manner. And if you like the content of the channel, then please do like, share and subscribe to the channel. And don't forget to visit the like button. So whenever we upload a new video, there will be direct notes considered. If any information in my lectures, then please look on the comment section. We will definitely include all those information in the coming lectures. So why do you waste more time? So let's get started. So you can see clearly here. So now we are going to learn about the first concept is sensitivity. So the first concept that we are going to learn is the sensitivity. So you can see clearly this is called as a block diagram. The control system is a basic block diagram. So the input is R of S and the output is C of S. So by default here we are always going to choose the negative feedback system. So this is a negative feedback system and this is positive and this is negative. So therefore this is the positive, this is negative. So therefore we can see this is called as a G of S. So G of S is called as a plant transfer function, whereas H of S is called as a feedback transfer function. So G of S is called as a plant transfer function and H of S is called as a feedback transfer function. So there is a negative feedback from output to input. There is a negative feedback, therefore this feedback, and the feedback transfer function is H of S, and this is a forward path transfer, because this is a plant transfer function is G of S. So this is a basic block diagram in the case of the control system. So what is the closed loop gain? The closed loop gain is M of S is equal to G of S by 1 plus G of S H of S. M of S is nothing but which is basically C of S by R of S. So therefore, whatever the closed loop gain, which is C of S by R of S is equal to basically, so we simply get it as M of S is equal to G of S by 1 plus G of S H of S. Here it is a negativeness, here it is a positive. Suppose here it is a positiveness, here we have to use the negative. So these things always will be keep in mind. So here it is a negativeness, here we have to use the positive symbol. Suppose if it is a positiveness, here we have to use the negative symbol. So this is called as the closed loop gain. The closed loop gain of the C, allowed and C of S by R of S is equal to M of S is equal to G of S by 1 plus G of S H of S for the negative feedback system. So now we are going to find what is the sensitivity of the M of S with respect to G of S. So what is the meaning of this one? Sensitivity, let's say the sensitivity of M of S with respect to G of S means, suppose if G of S is varying, suppose if any parameter in G of S, if it is varying, then what is the effect on the M of S? So that is the meaning of this one. So whatever the variation of G of S, so because of the variation of the parameters in G of S, then what is the overall change in the M of S? This is called as the sensitivity. So sensitivity of M of S with respect to G of S is equal to A. So basically the shortcut remember is here. So here G of S, right? So here also G of S. Here also G of S. Here is M of S means here it is M of S and here it is M of S. The shortcut to remember. So here G of S, here B into G of S, here M of S means here is M of S, here B into M of S. So this one always you have to keep in mind. So in this fashion always you have to keep in mind. So sensitivity of M of S with respect to G of S is equal to, you can say G of S by M of S into B into M of S by B into G of S. So always remember the formula sensitivity of alpha with respect to beta. So this formula always you have to keep in your mind. I already told you here beta means here also beta. Here B into beta. Here alpha means here it is alpha. Here B into alpha. So this one always you have to keep in mind. So like this. So like this. So this is something always you have to keep in mind. So therefore, sensitivity of M of S with respect to G of S is equal to G of S by M of S into B into M of S by B into G of S. So this one always should be kept in mind. So this is the standard formula. The sensitivity of alpha with respect to variation beta is equal to beta by alpha into B alpha by B beta. And shortcut remember is here alpha means here alpha, here alpha. Here beta means here beta, here beta. So this is basically derivative. So now we know M of S. So we know M of S. So do this derivative with respect to G of S, and then if you simplify, then again if you keep M of S and if you simplify, finally we are going to get which is sensitivity of M of S with respect to G of S is equal to 1 by 1 plus G of S H of S. So basically if you do derivative of D by mostly if you are going to do the M of S derivative with respect to G of S, you are going to get some result. Again where m of s would be this one result here. And if we simplify finally, we are going to get the result which is 1 by 1 plus g of s into h of s. So therefore, sensitivity of m of s with respect to variation in g of s is equal to 1 by 1 plus g of s h of s. So I will try to always take the negative value only. So this is called as the negative symbol. So the negative of sensitivity of m of s with respect to g of s is equal to 1 by 1 plus g of h of s. Take the negative value. So here basically we are taking only the negative value only, we are taking always into this account. So this formula always you have to keep in mind. So therefore, the log of the sensitivity of the m of s with respect to g of s is equal to the log of 1 by 1 plus g of s h of s. So this concept always you have to keep in mind. So now we will learn what is the variation of m of s with respect to variation in h of s. So what is that we are going to study here. So same way, the sensitivity of variation of m of s, the sensitivity of m of s with respect to variation in h of s is equal to same formula here. M of s means here m of s, here m of s. H of s means here h of s, here h of s. So this is basically derivative. So therefore, we can say h of s by m of s into derivative of m of s by derivative of h of s. So this formula always you have to keep in mind. So here m of s means here m of s, here m of s. H of s means here h of s, here h of s. So this is basically derivative. So now you know m of s. So you know the m of s. Just to the derivative of m of s with respect to h of s. So we are going to get some result. Again, you know the value of m of s here. They substitute here and if you simplify, finally, we are going to get the result which is the sensitivity of the m of s with respect to variation of h of s is equal to minus g of s into h of s by 1 plus g of s into h of s. I want to take only the negative part. So therefore, the negative of the sensitivity of m of s by m of s with respect to h of s is equal to just take the negative part. So this negative is going to become positive because we are taking the negative value. So therefore, negative of g of s into h of s by 1 plus g of s into h of s. So this is basically h of s. So this is basically h of s. So therefore, this form always will be repeated 9. So therefore, we can say the sensitivity of m of s with respect to g of s is equal to 1 by 1 plus g of s h of s. And the sensitivity of m of s with respect to h of s is equal to g of s into h of s by 1 plus g of s h of s. So always I am taking only the first value only I am going to take. So if you are going to compare these two equations, then what we can say, this value is higher when compared to this value. So therefore we can say sensitivity of m of s with respect to h of s, the negative part, I am taking only the negative part, is always greater than the negative of the sensitivity of m of s with respect to g of s. So in simple words, I can say only one thing. Suppose if any parameter is changing in the feedback, then the overall value changing in the output is very higher when compared to changing in the g of s. So if any parameter which is going to change the feedback transfer function, feedback part, then it is going to affect the overall output, which is somewhat more when compared to the change in the g of s. So this is what I am trying to tell you. So in simple words, I can say whenever any parameter in the feedback transfer function, if it is changing, then the output is going to change somewhat higher when compared to the variation in the parameter of the GFS plant transfer function. So this form is always you have to put in it, and so therefore we can say finally the sensitivity of m of s with respect to g of s is equal to 1 by 1 plus g of s h of s, and sensitivity of m of s with respect to h of s is equal to g of s into h of s by 1 plus g into h of s. I am telling on the negative part. So therefore the sensitivity of variation of m of s with respect to h of s is always greater than the sensitivity of m of s with respect to g of s variation. I am always telling you about it. So I am always taking into account regarding the negative values only I am going to consider. So now let's go for the other concept, which is, so basically this is for the closed loop transfer function. Suppose for the open loop transfer function, what is the sensitivity that we are going to calculate? So for the open loop transfer function, is there is no feedback. So there is no feedback. It is the input is R of s. So input is R of s and the output is C of s. And the plant transfer function is G of s. And there is no feedback part. So there is no feedback part. So therefore we can say because this is an open loop system. Then what is overall gain? Overall gain m of s is nothing but G of s. G of s is the overall gain, which is C of s by R of s. So it is C of s by R of s is the overall gain. So there is no feedback part, only G of s is there. So now I want to find what is the sensitivity of m of s with respect to G of s. Means if any parameter in the G of s is varying, And what is the overall sensitivity of M of S? I want to figure out. Sensitivity of M of S with respect to G of S. So say, I want to figure the formula. If G of S means here G of S, here G of S. Here M of S means here M of S, and here M of S. So therefore, we can say G of S by M of S into derivative of M of S by derivative of G of S. So you know M of S. So you know M of S. So therefore M of S of G of S. So B derivative of G of S with respect to derivative of G is this value is 1. And M of S is also G of S. So this value is also 1. This value is also 1. So 1 to 1 is equal to 1. So therefore, sensitivity of M of S with respect to G of S is equal to 1. So therefore you can say, so but in this case, see, you can see clearly here, denominator is higher when compared to numerator. Here 1 plus plus, the denominator is higher when compared to numerator. This one is always lesser than 1. So this one is always lesser than 1. Here also, if you see clearly, the denominator is higher when compared to numerator. So this one is also lesser than 1 because in both the cases, the denominator is higher when compared to numerator. The denominator is higher when compared to numerator. Therefore, we can say the overall values are always lesser than 1. In the case of closed loop system, but in the case of open loop system, this value is equal to 1. So therefore, simply, finally I can say only one thing. So the sensitivity of open loop system is always greater when compared to sensitivity of closed loop system. So therefore, suppose if any parameter is changing in G of S, any parameter is changing in G of S, then the overall changing in output is higher in open loop system when compared to closed loop system. So this is what I am trying to tell you. So if you are going to compare, you can say the sensitivity of open loop system, open loop system is higher than the sensitivity of the closed loop system. And this for always you have to keep in mind. In the case of sensitivity in the closed loop system, then we can say whatever the sensitivity of M of S with respect to H of S is always higher when compared to sensitivity of M of S with respect to G of S. So this one I already told you, this is in the case of closed loop system. So finally, I can say only one thing, which is in the case of closed loop system, the sensitivity of M of S with respect to G of S, the rapid value is 1 by complex G of S, H of S. Similarly, the sensitivity of M of S with respect to H of S in the case of closed loop system, the rapid value is G of S, H of S by 1 by G of S, H of S. Whereas in the case of open loop system, the sensitivity of M of S with respect to G of S is always equal to 1. And the sensitivity of open loop system is always greater than the sensitivity of the closed loop system. In the case of sensitivity in the closed loop system, the sensitivity of M of S with respect to H of S is always greater than the sensitivity of M of S with respect to G of S variation. So this points always you have to keep in mind. We are going to discuss the other concept, which is the transfer function. Suppose you can see clearly transfer function. So basically this is the LTI system. LTI system is, we can say it is a linear time invariant system. The system is going to satisfy two properties. One is the linear property and the time invariant property. That is the reason the system is said to be linear time invariant system. So you can see the input is R of S. So you can see the input is R of S and the output is C of S. So you can see clearly, you can say input is R of S and the output is C of S. So basically it is a standard notation. So input always we are going to represent by R of S and the output always we are going to represent by the notation C of S. Then what is the transfer function? The transfer function of the system is the Laplace transform of the output by the Laplace transform of the input. So this is the meaning of the transfer function. Transfer function means is a Laplace transform of the output by Laplace transform of the input under the assumptions that all the initial conditions are 0. So this is the definition of the transfer function. So transfer function means it is a ratio of the Laplace transform of the output signal by the Laplace transform of the input signal under the condition all the initial conditions are 0. Or you can say all the initial conditions are assumed to be 0 in the case of transfer function. So here, what is the output signal? C of t. And what is the input signal? R of t. So therefore we can say the transfer function is the Laplace transform of C of t by the Laplace transform R of t. So Laplace transform of C of t is nothing but C of s. And Laplace transform of R of t is nothing but R of s. So you can see clearly from this picture. So therefore, transfer function means the definition it says that it is a ratio of the Laplace transform of the output signal by the Laplace transform of the input signal under the conditions all the initial conditions are 0. So now the transfer function, the general notation is standard, and you can say the standard notation, which is basically transfer function is equal to C of s by R of s is equal to K into S plus Z1 into S plus Z2 and goes on by S plus P1 into S plus P2 and goes on. So this is called as the standard form, or you can say the standard form of representation of the classic function, where K is called as the system gain. So this is called as the standard form of the representation of the transfer function, where K is called as the system gain. And the numerator roots are called as the zeros, and the denominator roots are called as the poles. So this will always be keeping that. So the numerator roots are called as the zeros, and the denominator roots are called as the poles. So now you can say you can also represent this one in the other format also. We can try to represent in the other format also, which is so transfer function C of s by R of s is equal to Ks into 1 plus Ks into 1 plus Qs and goes on by 1 plus Qi into s into 1 plus Q2 into s and goes on. So if basically rearrange this one, you can get this one. If you rearrange this one, then you are going to get this one. So this is called as the time constant form of the representation of the transfer function. So this is the time constant form of the representation of the transfer function. So both are same. The only way we are going to representation is somewhat different. Here KDS is called as a system DC here. So KDS is called as the system DC here. So basically these two are a representation of the transfer function. So this is basically standard form and this is the time constant form. So we can get one thing from the other by easily doing a simplification. So this is called as the time constant form. Here KDS is called as the system DC gain. And the numerator roots are always called as the zeros, and the denominator roots are always called as the poles. So this one always you have to keep in your mind. So now the other concept is input on this Laplace transform. So basically in the case of control system, we regularly use few signals. So always you have to know the Laplace transform of these signals. Always you have to keep in your mind. So these are the signals which you always use in the control systems, and we definitely have to know all these transfer functions of these signals also. So what are the input signal that we use in the control system, which is R of t. R of t is the input signal, and the R of s is the transfer function of the input signal, which is R of s. So A into U of t is called as the step signal, and its transfer function is A by s. AT into U of t is a ramp signal, and its transfer function is A by, and its Laplace transform is A by s square. And A by 2 into t square, which is basically into U of t, and its transfer function is A by, and its Laplace transform is A by s square. And delta of t is called as the impulse, unit impulse signal, and its transfer function, and its Laplace transform is 1. So always you have to remember the Laplace transform of the power of n is always equal to 1 factorial by s the power of n plus 1. So based on this formula only, we have got all this, we can see the Laplace transform of all these signals. So A into U of t has Laplace transform U by s, and AT into U of t has Laplace transform U by a square, and U by 2 t square AT and Laplace transform U by a square, and the delta of t has Laplace transform 1. So these are the signals always we are going to use in the control systems. So always you have to know the Laplace transform of the signals, always you have to keep in mind. So this is called as the step signal, and this is called as the ramp signal, and this is called as the parabolic signal, and this is called as the impulse signal. So these things always you have to keep in mind. So this is a standard representation of the step signal, this is a standard representation of the ramp signal, and this is a standard representation of the parabolic signal. So this is basically the impulse signal. So all these forms always you have to keep in mind. The Laplace transform of the power of n is equal to n factorial by s the power of n plus 1. So by using this formula, we have got all these signals that correspond to Laplace transform. So now, what is the impulse response of the LTI system? So what is the impulse response of the LTI system that we are going to study? So basically, what is the meaning of impulse response of LTI system means? Suppose for this LTI system, suppose if I am going to choose the input as the impulse, then what is the response that I am going to give? Respond as the impulse response. If the input is the impulse input, then I have to give the impulse response. That is the meaning of this concept. So therefore, impulse response of LTI system is if the input you are going to give impulse input, the response is called as the impulse response. So basically, you can say this LTI system, and this LTI system has a transfer function G of s. This LTI system is having a transfer function G of s. and the input is delta of T. So you can say input is impulse input. So output is the impulse response, and the standard representation is h of t. So this is called as the h of t. So this is the standard representation. H of t is called as the impulse response, and delta of t is called as the impulse input, or you can say impulse signal. Then what is the transfer function? I already told you what is the transfer function. Transfer function is nothing but which is g of s. Transfer function is nothing but g of s. It is a ratio of the Laplace transform of output by the Laplace transform of input. And the Laplace transform of output is Laplace transform of h of t by Laplace transform of delta of t, which is equal to 1. So therefore we can say order this transfer function is always equal to the Laplace transform of the impulse response. So therefore, whatever the transfer function of the given system is always equal to the Laplace transform of the impulse response. So this would always be the keep for any system, its a transfer function is always equal to the Laplace transform of the impulse response. So therefore, we can say the transfer function is equal to g of s is equal to Laplace transform of output signal by Laplace transform of input signal. The output is h of t and input is delta of t. So Laplace transform of h of t by Laplace transform of delta of t. The Laplace transform of delta of t is always equal to 1. So therefore, we can say here is going to be is equal to Laplace transform of h of t. So therefore, for any system, the transfer function is always equal to the Laplace transform of the impulse response. H of t is the standard representation of the impulse response. So now, this is basically, we can say this is basically a system. A system has a transfer function g of s, and the input is r of s, and the output is c of s. And what is the transfer function? Transfer function g of s is equal to the Laplace transform of output by the Laplace transform of input. The output is here c of s, and the input is now r of s. So we can say now, if we rewrite this one, we are going to get c of s is equal to r of s into g of s. And g of s into r of s, r of s into g of s. You can get anything, and it is same. So these things always you have to keep in your mind. Therefore we can say finally, always you have to keep in your mind, which is that for any system, the transfer function is the Laplace transform of the impulse response, and c of s is always equal to r of s into g of s. As you can see clearly from this picture, we are going to discuss the other concept, which is the transfer functions for the compensators. So basically, we try to figure out the transfer functions for the different compensators that are going to present in the control systems. So basically, compensators are basically used for improving the transient response as well as the steady state response characteristics. So what is the basic agenda of the compensators? Compensators are basically used for improving the transient response as well as the steady state response characteristics. So basically, we can say the basic agenda of the compensators are basically used for improving the transient response as well as the steady state response characteristics. Means improving the transient response means decreasing the rise time. Improving the steady state response means decreasing the steady state error. So then basically, improving the transient response means decreasing the rise time, and improving the steady state response means decreasing the steady state error. So these are the basic agenda of the compensators. So basically there are three types of compensators. So there are basically three types of compensators, which are lead compensator, lag compensator, and lag lead compensator. So these are the three compensators which are going to be used in the control system, which is lead compensator, lag compensator, and the lag lead compensator. So therefore we can say compensators are basically used for improving the transient response as well as the steady state response characteristics. So improving the transient response means decreasing the rise time. Improving the steady state response means decreasing the steady state error. So basically there are three types of compensators in the control systems, which are lead compensator, lag compensator, and lag lead compensator. So lead compensator is always used to improve the transient response. So lead compensator is always used to improve the transient response, whereas the lag compensator is always used to improve the steady state error. So whereas the lag lead compensator it is used to improve both the transient response as well as the steady state response. So these things always you have to keep in mind. So lead compensator is always used to improve the transient response, whereas the lag compensator is always used to improve the steady response, whereas the lag lead compensator is used to improve both the transient response as well as the steady state response. So how do we remember this one? See, here lead has 4 returns, here lag has 3 returns. So when compared to gradual and steady, gradual does more votes when compared to steady. So large two things of more votes and large two things of less votes. Between these two, lead has more. So between these two, this has more. So large two things of more votes, large two things of less votes. So therefore we can say lead company is always used to improve the gradual response, and the lag company is always used to improve the steady state response, and the lag company is always used to improve both the gradual response as well as the steady state response. So now we will discuss each and every composite in a very detailed manner. So the first composite that we are going to study is the lead compensator. So this is a circuit diagram of the lead compensator. So you can see clearly this is a electrical circuit, this is the resistor, this is the capacitor, this is the resistor. So R1 in the terms of this thing, you can see the circuit in the Laplace transform. We are going to get this is R1, this is 1 by S7, is R2. So input is Vi of S and output is V of S, and the current is I of S. So if we try to figure out the transfer function V of S by Vi of S, finally we are going to get in this formula, which is equal to K into 1 plus 2S by 1 plus alpha 2S. So in this formula, we are going to see the transfer function. So in this formula, we are going to see the transfer function. Here K is called as the constant. So K is the constant we are going to get. And this alpha is nothing but we are going to get, which is equal to R2 by R1 plus R2. So alpha we are going to get is equal to R2 by R1 plus R2. So you can see denominator is higher and compared to numerator. So therefore alpha value is also less than 1. And the time constant K is nothing but which is R1 C1. So this is a time constant means R1 C1. And K is a constant and alpha is R2 by R1 plus R2. So these two follows you have to keep in mind. Time constant K is nothing but R1 C1 and alpha is nothing but which is R2 by R1 plus R2. So in the case of alpha, the denominator is higher in compared to numerator. So definitely alpha value is always less than 1. If K is a constant. So now if we plot the 0 and a 4, so numerator root is called as 0 and the denominator root is called as 4. So what is the numerator root 0? So 0 is something which is equal to minus 1 by 2 and the 4 is something but which is equal to minus 1 by alpha 2. So now if you see clearly alpha is lesser than 1 means the denominator is lesser. So therefore overall value will be origin higher means very far from origin. So this is a 4 and this is a 0. So minus 1 by alpha to minus 1 by 3. This is minus 1 by 3. So you can see alpha is lesser means the denominator is very lesser. So therefore overall value will be very higher. So 4 will be far away from origin when compared to 0. So that's why we can say that in the case of lead compensator, the 0 will be very closer to origin when compared to 4. So this is in the case of lead compensator. In the case of lead compensator, 0 will be always closer to origin when compared to 4. So basically, the shortcut remainder is basically you can see, suppose if it takes some point P here, so if you draw a straight line like this, it is going to make some angle theta 1. Suppose if the same if you draw from here, we are going to get an angle theta 1. So definitely you can see theta 1 is always higher than theta 2. So therefore, you can see this is that theta 1 is always greater than theta 2. So if this theta 2 goes to the upper part, it will become negative. Therefore, theta 1 minus theta 2. As far as greater than theta 2, this value will be always positive. Therefore, you can say, so we are going to get the positive. Positive means we can say basically lead compensator. So, lead compensator means always output is going to lead the input. Output value is going to lead the input. So, what is the output? Your input is going to lead the input. So, positive means value is positive means the output is going to lead the input. So, these things are always going to keep it down. So, therefore, we can say the output is always going to lead the input. So, therefore, 0 is always closer to origin when compared to 4. 0 is very closer to origin when compared to 4 in the case of lead compensator. So now, if you see clearly, it is also called as, this lead compensator is also called as the high pass filter. It is also called as the high pass filter. Why it is like this? See, 0 is going to come earlier. So 0 is going to come earlier means 0 means plus 20, plus 10 decibels per decade. Then what is going to happen? Then this one is going to come. Just 0 means plus 20, plus 20. Then this one is going to come, which is nothing but 4. 4 is going to come. 4 means we can say minus 20. Minus 20 means the already plus 20 is there. If you are going to have minus 20, so plus 20 minus 20 is 0. So you are going to get a high pass filter. So therefore you can say this is basically high pass filter. So actually we are going to get 0 means plus 3 decibels per decade. And then we are going to get the 4, which is minus 7 decibels per decade. So plus 20 minus 20 nothing. Total value we are going to get 0. So this is the 0 dB. So this is nothing but high pass filter. So here it is also called as a high pass filter. It is also called as a PD controller. So basically, if you are going to plot the polar plot, this graph is going to lie only in the first coordinate. So if you are going to plot the polar plot, then the graph is always going to lie in the first coordinate always. So these things always you have to keep in mind. So wave controller is also called as a high pass filter. It is also called as a PD controller. And if you are going to plot the polar plot for this wave compensator, always the polar plot is always going to lie only in the first coordinate. So because of this wave compensator, I've already told you, wave compensator is always used to improve the transient response. Transient response means the rise time is going to get decreased. So I've already told you the rise time is going to get decreased. So damage is going to get increased because rise time to damage is always equal to constant. So as rise time to damage is equal to constant, as rise time decreases, then the damage should increase. As Stoichiometry is always constant, means it is not going to affect the steady state error. So it will be remaining as same as the previous one. So it will never increase or it will never decrease. It will remain as it is. So therefore we can say the Stoichiometry is equal to constant, and it is going to increase the wave crossover frequency. So it is going to increase the wave crossover frequency, and it is also going to affect the damping ratio as well as the natural frequency. So these are the things which are going to get affected because of this wave compensator. So because whenever we are going to add the wave compensator we can say in a control system, or we can say basically in a control system, then we can say the rise time is going to get decreased and the bandwidth is going to get increased and the temperature is constant and the gain crossover frequency is going to get increased and the zeta value is also going to get affected and the natural frequency is also going to get affected. So these are the changes we can see whenever we are going to add the wave compensator in a block diagram. So now let's go for the flat compensator. So what I told you, flat compensator is always used to improve the steady response. Steady response means it is going to decrease the steady state error. So this is the circuit diagram for this flat compensator. So if you are going to compare these two things, we can usually say whatever this capacitor, so this capacitor we have removed it and we have put here, everything is same. So just we have compared this capacitor and we take this capacitor in series with respect to R2, then we are going to get this flat compensator. Therefore you can see this is R1, this is R2 and this is 1 by SC2. So whatever this capacitor, just we have cut it down and we have kept it series with respect to R2. So this is the circuit we are going to get. So output we have taken here, input we have given here. This is A of S, this is R1, this is R2, this is 1 by CS2, and 1 by SC2 in terms of Laplace domain. And this is unit of S. So if we try to figure out the unit of S by D of S with the help of, we can say for the Holder division principle, we are going to get unit of S by D of S is equal to K into 1 plus Ts by 1 plus beta Ts. So basically, you can either use beta or either you can use alpha, and now it is same. The concept is same. You can use either beta or either you can also use alpha. But I will try to always use alpha only because it may confuse you. Sometimes you are using alpha, sometimes you are using beta. It may confuse you. But I will try to always use the alpha. But here, okay, it's okay. And now we are going to use beta. So always beta into PS. We also have beta, which is reciprocal of the previous one. So reciprocal of the previous one, which is there is R to the R of this R2. So now it will become R of this R to the R2, reverse of the previous one. So therefore, it is equal to R of this R to the R2. So you can see clearly the numerator is higher when compared to denominator. So therefore, beta value is always greater than 1 in this case. And K is always equal to constant. The time constant is now R2 into C2. In the previous case, the time constant is R1 C1. But here the time constant is R2 C2. So therefore, we can say here you can say simply. So basically I will try to use alpha only. So here I am going to use here alpha only. Here I am going to use alpha. It's just a notation. So the just notation I will try to use alpha. So therefore we can say clearly and what is going to happen in this case. In this case, alpha is equal to, can say, reverse of the previous one, which is, we can say R1 is R2 by R2. So therefore alpha is always greater than 1 in this case. And K is always equal to constant. And time constant is equal to R2 C2 in this case. So now, what is a 0? 0 means the new roots are called as a 0, which is equal to minus 1 by 2. And the without root is called as 2, is equal to minus 1 by alpha 2. So we try to use alpha always. Anyway, the concept is same. Anyway, the concept is same. The only thing is you have to eliminate the concept. Now here alpha is greater than 1. Alpha is greater than 1 is if they have this more, so all value will be very lesser. So 4 is very near to origin when compared to 0 in this case. So minus 1 by alpha 2 is minus 1 by 2. So you can see clearly from this picture. So therefore, finally you can say this is the S plate. So if you want to remember, the easy way is the lab compulsory means always the output is going to lag the input. The output is always going to lag the input. So output is always going to lag the input in the case of lag compensator. Suppose if you are going to, so for simple analysis, take at some point P. Take at some point P. So we take this angle, so this basically you can say theta 1. And this angle is theta 3. So remember this is always 0. Number is always 4. So angle is theta 3 by theta 1. So theta 1 is always greater than theta 2 in this case. So if this angle goes up, it will become theta 2 minus theta 1. As theta 1 is greater than theta 2, so this angle is negative. So negative means we can say the whole angle is negative means we can say the output is going to lag the input. If the whole angle is positive means the output is going to lead the input. If the whole angle is negative means the output is going to lag the input. So your negative means the output is going to lag the input. So therefore you can say the pole is closer to origin compared to 0. So now you can say the always you have to keep in your mind, which is in the previous case the alpha is nothing but which is R2 by R1 plus R2. Here it is a first one which is R1 plus R2 by R2. The time constant is R1 C1. The time constant is R2 C2. So these things always you have to keep in your mind. The transfer function in addition are in same manner. So you don't have to confuse. Always you have to use alpha for both the cases. But if you know the concept, you can use alpha for both the cases. So now, what is going to happen? So this is basically it is also called a low pass filter because now what is going to come earlier? The pole is going to come earlier. Pole means we can say, so pole means we can say simply pole is means minus 20. So minus 20 is fixed up VK. Then 0 is going to come minus 20. So 0 is plus 20. Already there is a minus 20. So minus 20 plus 20 is nothing but 0 dB. So this is a 0 dB. So like this you are going to get. So this is a low frequency only get passes through this block diagram. So only the low frequencies are going to pass through this circuit, but not the higher frequencies. So this is also called as a low pass filter. And this is also called as a gate controller. And whenever you are going to draw the polar plot, so whenever you are going to draw the polar plot for this lag compensator, always it is going to lie in the fourth corner. So whenever you are going to draw the polar plot for this lag compensator, it is always going to lie in the fourth corner. So therefore you can say this lag plot is also called as a low pass filter. It is also called as a PI controller. And whenever you are going to draw the polar plot for this lag compensator, it is always going to lie in the fourth corner. So because of this lag compensator, so whenever you are going to include the lag compensator in the control system, then what are the changes we can see, which is the gain crossover frequency, the gain crossover frequency will decreases. In the previous case it will increase, but now it will decrease. And the rise term will increase here. The rise term will increase. And zeta value will be constant. And the omega will be constant. And the bandwidth will decrease. So if you are going to compare, you can see the rise time is decreases means your rise time will increase. As rise time increases, bandwidth will decrease because rise time in the bandwidth is always equal to constant. So therefore, as the rise time increases, the bandwidth should decrease. So these things always you have to keep in mind. Here zeta and omega changes, but here both are constant. Here zeta is equal to constant and omega is also constant. In the previous case, both are changing means here it will be constant in this case. And here omega GC increases means that omega GC will decrease. Omega GC will decrease. And also the steady state error is also going to be decreased. So this is the basic agenda. So this is the basic agenda This is a basic agenda of this lag compensator in order to decrease the steady state error. So here the steady state error will also decreases. So these are the changes you can see by using the lag capacitor. So listen carefully. The rise time will increase. As the rise time increases, definitely bank will increase because rise time demand is always equal to constant. In the previous case, zeta and omega changes. I should inform that here, zeta and omega are always equal to constant. The basic idea of this one is to decrease the steady state error. So sorry, the steady state error is also is going to decrease. So whenever this increase means omega this will decrease. So this is always you have to keep in mind. So this is somewhat right transfer of this previous case. So now we will study regarding the lag lead compensator. So now we are going to study the lag lead compensator. So this is the circuit. It is lag lead compensator. So to see clearly, which is basically this video, this is basically lead compensator and this is the lag compensator. Just we are going to combine these two circuits. This is the lead compensator, lag compensator. We are going to club it. Then we are going to get the lag lead compensator, which is R1, C1. R2, C2. This is your parallel, this is your series. So R1, 1 by SC1, R2, 1 by SC2. The input is A of S and output is delta of S. Just we have club this or mix these two circuits. Then if you try to figure out the V of delta of S by V of S, transfer function output by input, then we are going to get finally K into 1 plus P1S into 1 plus P2S by 1 plus alpha P1S into 1 plus beta P2S. So here I am going to use beta. Here anyhow it is same, even if it concept. So I already told you for the lead capacitor, what is the value of alpha? Alpha is equal to R2 by R1 plus R2. And T1 is equal to R1 C1. Just now we have seen. For the lag capacitor, beta is equal to reciprocal of this one, which is R1 plus R2 by R2. And D2 is equal to R2 C2. So this is for the lead compensator and this is for the lag compensator. Just now we have seen. So this is for the lead compensator and this is for the lag compensator. For the lead compensator, alpha is equal to R2 by R1 plus R2 and alpha value is lesser than 1 because T1 is higher than numerator and T1 is equal to R1 C1. In the case of lag compensator, beta is equal to R1 plus R2 by R2. Here denominator is lesser than complete numerator, so this ratio is greater than 1 and D2 is equal to R2 C2. So now we are going to plot the 0 as well as 1. So what is a 0? So zeros are nothing but. So zeros are nothing but minus 1 by P1 and minus 1 by P2. So what are the poles here? Poles are minus 1 by alpha P1 minus 1 by beta P2. So these are the things we are going to get here. So now I am going to plot all these things on this S plane. Poles are zeros. So what are the zeros? Zeros are minus 1 by P2 minus 1 by P1. So you can see minus 1 by P2, minus 1 by P1. And the poles are minus 1 by alpha P1, minus 1 by beta P2. So you can see clearly alpha is lesser. Alpha is lesser. Alpha is lesser means denominator is very, very lesser. So overall value is very, very higher. It will be always 4. And here beta is greater than 1. So if beta is greater than 1 means this ratio will be as beta is greater than 1. So this denominator is very higher. So overall value will be very, very lesser. So this is the way that we are going to get. So these are nothing but. These are nothing but basically these are lag compensator. So these are lag compensator. So this belongs to lag compensator. So you can see clearly this part is going to belongs to lag compensator and this part is going to belong to lead compensator. So now if you are going to travel in this direction, the first thing that we are going to see is the lag and then we are going to see the lead, and that is the reason it is called as the lag lead compensator. So listen carefully. If we are going to travel in this direction, the first thing that we are going to see is the lag compensator and then we are going to see the lead compensator. So this is called as the lag lead compensator. This is the reason it is called as the lag lead compensator. So therefore, whenever we are going to move in this direction, the first thing that we are going to see is the lag compensator and then we are going to see the lead compensator. So because of this reason only, it is called as the lag lead compensator. So now this lag lead compensator is always used to improve both the transient response as well as the steady state response. So this is also called as a band reject filter. So as you see, initially you are going to get the pole means minus 20 decibels per decade. You are going to get like this. Then again we are going to get the 0. So minus 20 plus 20 something to 0 dB. We are going to get 0 dB. Then again plus 20. So we have plus 20 is again like this, plus 20 maybe we are going to do. Again there is a pole. Pole is again minus 20. So plus 20 minus 20 is again 0 dB. So this is what we are going to do. So this is these are past, these are past. So these frequencies are past, these frequencies are past. But not these frequencies. So this is called as a band reject filter. So therefore this is called as a lag of is also called as a band reject filter. And is also called as a PID controller. It is also called as a PID controller. So it is also called as a PID controller. So if you see clearly in a shortcut, in the case of very compensator, D is there. It is also called as a PD controller. In the case of lag, there is no D. It is called as a PID controller. So basics always you have to keep in mind. In the case of very compensator, D is there. So it is used for PD. Then lag is used for PID. So lag is used for PID. It's a shortcut to remember. So therefore we can say in the case of very compensator, D is there. So therefore it is also called as a PD controller. Then lag compensator is also PID controller. Then lag compensator is also called as a PID controller. So these things always you have to keep in mind. We are going to discuss another concept, which is the transfer function for the mechanical systems. Means we are going to figure out the transfer functions for the different mechanical systems. So the first one is the mechanical translation system. So mechanical translation system is, suppose if you take a small example of a birva in your home. So whenever you are going to push the birva, it is going to move in a straight line. So that is called as a mechanical translation system. Whenever anything object is moving in the one direction, so you can see in the straight direction, that is called as the mechanical translation system. So for the mass element, so you can see for the mass element, suppose here there is a mass m which is attached to a body like this. So for mass m, suppose if I am going to move this mass with the help of this force, so in this direction I am going to move this mass. If I am going to move this mass in the direction of the force, then definitely it is going to move some distance, means it will have some displacement, and also this mass is going to have some velocity. So whenever I am going to apply a force on this mass in this direction, so definitely it is going to move, so it will have some displacement, and also it will have some velocity by which it is going to get moved. So what is the equation? F is equal to, basic formula, F is equal to m into a. Force is equal to mass into acceleration, but acceleration is equal to rate of change of velocity. So A is equal to dv by dt. And when velocity is the rate of change of displacement, so therefore we can say if the velocity is equal to rate of change of displacement, then dv by dt is nothing but e square x by dt square. So these are the different ways that you can write the equation, which is force is equal to mass into acceleration, or force into to dv by dt, or force into d square x by dt square. So in any of this manner you can write. So therefore we can say F is equal to m into a, or m into dv by dt, or m into d square x by dt square. So this is for the mass element. Suppose for the damper element, means you can see clearly. So this is the pictorial representation of the damper element. So let me assume it is having some velocity v1, and it is see I am going to apply a force on this damper element in this direction. So I am going to apply some force on this damper element in this direction. So this junction will have velocity v1 in this direction, and this junction will have some velocity v2 in this direction. So therefore this will have some displacement x1 in this direction, and this will have some displacement x2 in this direction. So what is the overall force? The force formula is equal to B into v1 minus v2. So v1 minus v2 means from here to here, from tail to arrow. So F is equal to B into v1 minus v2 is equal to, but velocity is equal to rate of change of displacement. So therefore V into v1 I can write d by dt of x1, and v2 is d by dt of x2. So if you take d by dt common, then we are going to get B into d by dt of x1 minus x2. So where B is called as a damper constant, or you can say damping constant. So B is called as a damping constant. So always remember F is equal to B into v1 minus v2, whereas v1 is equal to dx1 by dt, and v2 is equal to dx2 by dt. So if we take d by dt common, then we are going to get F is equal to B into d by dt of x1 minus x2. So these things always you have to keep in your mind. So for the spring element, so this is the spring here. So spring will have some spring constant, which is denoted by K, and this is a And we can say this is going to have some velocity v1 and this will have velocity v2. So whenever you are going to apply force of F on the spring, so in this direction, then definitely this will have some velocity v1, this will have some velocity v2, and this will have some displacement x1, and this will have some velocity, some displacement x2. So what is the force formula? F is equal to k into x1 minus x2. So F is equal to k into x1 minus x2. So you can, I've already told you velocity is the rate of change of displacement. So displacement is the integration of the velocity. So x1 is nothing but integration of v1 dt, and x2 is integration of v2 dt. So if you take integration common, we are going to get k into integration of v1 minus v2 into dt. So this is all about the mechanical translation system. So I can read it like this, which is F is equal to m into a or m into dv by dt or m into d square x by dt square. Here F is equal to b into v1 minus v2 or b into d by dt of x1 minus x2. Here F is equal to k into x1 minus x2, or we can say k into integration of v1 minus v2 into dt. So this is all about the mechanical translation system. Now let's go for the mechanical rotational system. So now let's go for the mechanical rotational system. Is the body is going to get rotated. So whenever you are going to apply any force in a body, if it is going to rotate, that is called as the mechanical rotational system. So now listen carefully. Here we are going to discuss about the inertia element. Inertia element means here J is called as the inertia of this body. So now I am going to apply a torque on this. If I am going to apply a torque, so basically torque like this. Basically the torque is basically in this direction torque, but let me assume in this manner, and here which is same. So if I am going to apply a torque in this direction, so omega is also in this direction and theta is also in this direction. So therefore we can say whenever I am going to apply the torque in this direction, so omega is also in this direction, theta is also in this direction. Whether I can represent in this manner or in this manner, and here which is same. So just for the easy way manner, I have written in this manner. But actually, the torque in this direction, omega is also in the same direction, theta is also in the same direction. So what is the formula? T is equal to, I have already told you torque is equal to moment of inertia into acceleration, which is alpha. But alpha is equal to rate of change of angular velocity, which is d omega by dt, and omega is the rate of change of displacement. Displacement is here theta. Omega is the angular velocity and t is the torque and j is the inertia. So t is equal to I into alpha, but alpha is equal to d omega by dt and omega is equal to d theta by dt. So if you simplify finally you are going to get t is equal to j into alpha or j into d omega by dt or j into d square theta by dt square. So this is for the inertia element. Now let's go for the damper element. So this is the damper element, same thing as the previous case. So I am going to apply the torque T in this direction. So this is having a angular velocity of omega 1 in this direction, and this is having an angular velocity of omega 2 in this direction, and this is having an angular displacement of theta 1 in this direction, and this is having a angular displacement of theta 2 in this direction. Then what is the formula? Then T is equal to B into omega 1 minus omega 2. You know omega 1 is d theta 1 by dt and omega 2 is d theta 2 by dt. So if we simplify, we are going to get b into d by d theta of d by dt into theta 1 minus theta 2. So this is same as the previous case. So T is equal to b into omega 1 minus omega 2 or b into d by dt of theta 1 minus theta 2. Then for the spring element, so this is the spring constant K. So if I am going to apply the torque in this direction, then this is the angle with displacement theta 1 in this direction, and this is the angle with displacement theta 2 in this direction, and this is the angular velocity omega 1 in this direction, and this is the angular velocity omega 2 in this direction. Then what is the overall torque? Torque T is equal to K into theta 1 minus theta 2, which is equal to K into, displacement is integration of the angular velocity. So therefore theta 1 is integration of omega 1 into dt, and theta 2 means integration of omega 2 into dt. So if we take integration common, we are going to get K into integration of omega 1 minus omega 2 into dt. So these formulas always you have to keep in your mind. So therefore I can say simply these formulas always you have to keep in your mind, which is T is equal to I into j into alpha or j into d omega by dt or j into d square theta by dt square, or then t is equal to b into omega 1 minus omega 2, which is equal to b into d by dt of theta 1 minus theta 2. Here t is equal to k into theta 1 minus theta 2, or k into integration of omega 1 minus omega 2 into d theta. So these formulas always you have to keep in the mind. We are going to study about the analogous system. So basically analogous system means, what is the meaning of analogous system? See, basically we are going to study different circuits in different domains, and then we are going to analyze their equations. So if you see clearly, their equations are also same. They are going to represent in the same format. See, if any two systems, if their equations are similar in nature, then those systems are called as the analogous system. So we can say, suppose if there are two systems in two different domains, if these two systems have the same equations in the same format, then we can say those systems are said to be analogous system. So now we will discuss about the different types of analogous systems. So in the mechanical translation system, so this is the, we can say a system is there here. So this is the mass M, this is the damper element, and this is the spring element we are going to keep, and this is the mass element. So for this mass element, if I am going to apply a force F, then what is the overall equation we are going to write? So net force is equal to mass into acceleration. If this is the direction of the force, then definitely these two forces are in the opposite direction. So net force is F minus this force is equal to mass into acceleration. So if we realize this one, we are going to get F is equal to this force plus mass into acceleration. So same thing I have written. So F is equal to m into dv by dt plus b into v plus k into integration of v into dt. Or we can write in the format of the velocity is equal to rate of change of displacement. So if we apply here, we are going to get F is equal to m into d square x by dt square plus b into dx by dt plus k into x. So these things always you have to keep in mind. So F is equal to m into acceleration means theta change of velocity. So m into d by dt plus b into v plus k into integration of v into dt. So velocity is equal to rate of change of displacement. So if you simplify, we are going to get F is equal to m into d square x by dt square plus b into dx by dt. If velocity is the rate of change of displacement, then integration of x is nothing but which is velocity. This integration of velocity is nothing but which is equal to x. So therefore we can say finally, so this is k into x. So this is the things that we are going to get from this system. Now let's go for the rotational system. For the rotational system, if I am going to apply a torque in this direction, it is going to have some displacement theta. And with displacement of theta, that k is a spring constant and b is the damping coefficient, then what is the overall equation that we are going to write for this equation? For the system, just p is equal to j into alpha on the side of change of angular velocity, j into d omega by dt plus b into omega plus k into theta means integration of omega dt. K into integration of omega dt means k into theta. Theta is the integration of angular velocity. So we are going to get, so angular velocity is the rate of change of displacement. So omega is equal to d theta by dt. Then we are going to get T is equal to j into d square theta by dt square plus b into d theta by dt plus k into theta. So these are the different ways of writing the equations. So for the system, we can say T is equal to j into d omega by dt plus b into omega plus k into integration of omega into dt, or T is equal to j into d square theta by dt square plus b into d theta by dt plus k into theta. Because angular velocity is the rate of change of angular displacement. So by using this formula, we have got this equation. Now let's for the series RLC circuit. For a series RLC circuit means inductor, resistor, capacitor. Here we are going to apply voltage source of V and the current is I. So what is the overall voltage? Overall voltage is the voltage drop across these three elements, which is supply voltage V is equal to voltage drop across the inductor plus voltage drop across the resistor plus voltage drop across the capacitor. So V is equal to voltage drop across the inductor is L into di by dt, and the voltage drop across the resistor is I into R plus voltage drop across the capacitor. I is equal to C dv by dt, and V is nothing but 1 by C integration of I dt. 1 by C integration of I dt. So this is the overall, we can say the equation, KVL equation for this system. So I is nothing but current is the rate of change of charge. Current is the rate of change of charge, means I is equal to dq by dt. So if you apply, we are going to get V is equal to L d square q by dt square plus R into dq by dt plus. If current is the rate of change of charge, then integration of current is nothing but which is equal to charge. So q by C. So these are the equations that we are going to get for this series RLC circuit. Now for the parallel RLC circuit, so you see resistor, capacitor and inductor, all these three elements are connected in parallel, and V is the overall voltage across these three elements, and here we are going to supply current source of I value. Then what is the, by KCL we can say the net current is the summation of the net incoming current is equal to net outgoing currents. So therefore the supply current is equal to current to this capacitor plus current to this resistor plus current to this inductor. So I is equal to current to the capacitor is C into d by dt, current to the resistor is V by R, and current to the inductor, V is equal to L dI by dt. So I is nothing but 1 by L integration of V dt, 1 by L integration of V dt. So this is the overall equation for this system. So voltage is nothing but rate of change of flux. So voltage is nothing but the rate of change of flux. V is equal to d phi by dt. So if you apply here, we are going to get I is equal to C into d square phi by dt square plus 1 by R into d phi by dt plus phi by L. So this is the equation that we are going to get for this one. So if you compare all these equations, then what we are going to get? So if you see clearly, note the relative velocity is the rate of change of displacement, means V is equal to dx by dt, and the current is the rate. So then omega, angular velocity is the rate of change of angular displacement. Omega is equal to d theta by dt, and current is the rate of change of charge. I is equal to dq by dt, and the voltage is the rate of change of flux. So V is equal to d phi by dt. So if you see clearly, all are in the same format. So all these equations are basically in the same format, as you can see clearly from this picture. So now what we are going to do? So we are going to analyze. All these equations now. We are going to analyze one after the another. So if you see clearly, we can say one important thing. All these equations are going to look in the same format. So now we are going to compare all these equations. If we compare all these equations, so comparing all these equations, then we are going to get, this is a mechanical system, this is a rotational system, this is a series system, and this is a parallel system. So here F, here T, here B, and here I, all are same. All are, we can say, analogous. So force is analogous to torque, and torque is analogous to voltage, and the voltage is analogous to current. Similarly, now mass is analogous to moment of inertia. Moment of inertia is analogous to inductor, and inductor is analogous to capacitor. So this you can see clearly from this one. Again, here we can say damping coefficient is analogous to resistance is analogous to conductance of reciprocal of resistance. Similarly, here K, spring constant is analogous to 1 by capacitance, and it is analogous to 1 by inductance, means inverse of capacitance and inverse of inductance. So spring constant is analogous to spring constant is analogous to inverse of capacitance, and inverse of capacitance is analogous to inverse of inductance. And here velocity, so here velocity is analogous to angular velocity, and angular velocity is analogous to, we can say, current. Current is analogous to voltage. Similarly, here angular displacement, here linear displacement is analogous to angular displacement, and angular displacement is analogous to charge, and the charge is analogous to flux phi. So these things that we are going to get from all these four equations. So finally I can say force is analogous to torque is analogous to voltage, and the voltage is analogous to current. Similarly, mass is analogous to moment of inertia. Moment of inertia is analogous to inductor, and the inductor is analogous to capacitor. And the damping coefficient is analogous to damping coefficient. Damping coefficient is analogous to resistor, and the resistor is analogous to irreversible of resistance of conductance. And here spring constant is analogous to spring constant. Spring constant is analogous to one inverse of capacitance. Inverse of capacitance is analogous to inverse of inductance. Here linear velocity is analogous to angular velocity. Angular velocity is analogous to current, and current is analogous to voltage. Linear displacement is analogous to angular velocity, angular displacement, and displacement is analogous to charge. Charge is analogous to flux. So these things always you have to keep in your mind. So same thing I have written. So by comparing the equations for the different types of systems, for mechanical system, for rotational system, for series system, and for parallel system. So these things we have got, which is force analogous to torque, torque is analogous to voltage, and the voltage is analogous to current. Mass is analogous to moment of inertia. Moment of inertia is analogous to inductor. Inductor is analogous to capacitance. Damping coefficient is analogous to damping coefficient. Damping coefficient is analogous to resistor, and resistor is analogous to reciprocal of resistance or conductance. Spring constant is analogous to spring constant. Spring constant is analogous to inverse of capacitance. Inverse of capacitance is analogous to inverse of inductance, reciprocal of inductance. Linear velocity is analogous to angular velocity. Angular velocity is analogous to current, and current is analogous to voltage. Linear displacement is analogous to angular displacement. Angular displacement is analogous to charge, and charge is analogous to flux. So these are the analogous quantities in each and every domain, for mechanical domain, for rotational domain, for series domain, and for parallel domain. So these things always you have to keep in your mind. Now we are going to discuss the another concept, which is called as the gates. So what is the concept of gates? Basically, these are used for either stepping up or stepping down, either torque or speed. So this is a basic agenda of the gates. These are used for stepping up or stepping down, either torque or speed. Means they can either increase the torque, or either they can increase the speed, or either they can decrease the torque, or they can decrease the speed. This is the basic agenda of the gates. Means they can increase the torque or decrease the torque, or increase the speed or decrease the speed. This is the basic agenda of the gates. So these are used for stepping up or stepping down, either the torque or speed. So you can see these are the two gates. You will have some teeth. So this is basically gates, means these are the teeth here. So the teeth here is N1. N1 means N1 number of teeth are present in this gear. And here R1 is the radius of this gear, the radius of this gear. And here N2 is the number of teeth are present on this gear 2. And R2 is the radius of this gear. And here we are going to apply torque in this direction. So whenever you apply torque in this direction on this gear 1, so it is going to rotate in the same direction with displacement of θ1. If this is going to move in this direction, then this will move in the reverse direction. So therefore, because of we can say these gears are always going to move in the opposite direction. If one is in the clockwise, means other will rotate in the anti-clockwise. So this is the basic agenda of this one. So therefore, now what is going to happen? So I am going to apply the torque P1 in this gear. So it is going to rotate in this direction θ1. So this will move in the reverse direction. So it will move upward with a torque of T2 with the displacement of θ2. So now we have to find what is the relation between these two things we need to figure out. So always you have to remember, which is N1 by N2 is equal to T1 by T2 is equal to R1 by R2. Shortcut is NTR, NT Ramarao. So NTR. N1 by N2 is equal to T1 by T2 is equal to R1 by R2. So this is the thing always you have to keep in your mind. And whatever the work in the first is always equal to work in the second case. So whatever the work done in the first case is always equal to work done in the second case. This is basically like a transformer. So overall power is saving both the input as well as output. Only the voltage and the current are going to get changes. Same thing here also. Only work is going to remain constant. Only the torque and the speed are going to get vary. The work is always constant. Which is work is equal to work formula is work is equal to torque into angular displacement. So therefore work is equal to T1, theta 1 is equal to T2 into theta 2. So this is the formula always you have to keep in your mind. So work is equal to T1 theta 1 is equal to T2 theta 2. So you know T1 by T2 is nothing but which is theta 2 by theta 1. So T1 by T2 is nothing but theta 2 by theta 1. If theta 2 is nothing but d omega by dt, theta 1 is nothing but d omega, T2 means d omega 2 by dt, theta 1 means we can say that is d omega 1 by dt. So if we do the ratio, we are going to get omega 2 by omega 1. So now angular velocity is always directly proportional to acceleration also. So alpha 2 by alpha 1. So you can see clearly what we can say, NPR, N1 by N2 is equal to T1 by T2 is equal to R1 by R2. So you know T1 by T2 is nothing but theta 2 by theta 1. So theta is directly proportional to, you know, theta is directly proportional to omega and omega is proportional to alpha. So these things always, you know, so therefore we can say theta 2 by theta 1 is equal to omega 2 by omega 1 is equal to alpha 2 by alpha 1. So these things always you have to keep in your mind. So therefore we can say shortcut to remember is NPR means N1 by N2 is equal to T1 by T2 is equal to R1 by R2. We know work is equal to T1 theta 1 is equal to T2 theta 2. So T1 by T2 is nothing but theta 2 by theta 1. But theta is the proportional to omega. Omega is the proportional to alpha. So therefore theta 2 by theta 1 is equal to omega 2 by omega 1 is equal to alpha 2 by alpha 1. So these things always you have to keep in your mind. So now special case, what is going to happen? Suppose if N1 is greater than N2, yes, in the gear 1, the number of teeth higher when compared to second gear, then what is going to happen? If N1 is greater than N2, then what is going to happen? See, if N1 is greater than N2, then T1 is always greater than T2. So you can get from this one. So therefore, T1 is greater than T2. Then if N1 is greater than N2, it indicates that omega 2 is greater than omega 1. It indicates that omega 1 is also less than omega 2. So this is also you can say. So therefore, listen carefully, if T1 is greater than T2, then we can that omega 1 is less than omega 2. So this is what we are going to get. I have already told you, as the power is equal to working voltage into current. As the voltage increases, then current will decrease. Then only power is equal to constant. If torque is increasing means angular velocity should decrease. Then only their quantity is a constant. If torque is increasing means here this one will decrease. So therefore you can say here as the torque increases, the angular displacement decreases, so angular velocity also decreases. As the torque increases, then angular velocity, as the torque increases, then definitely you can say that. So you can see clearly as the torque increases, then angular velocity should decrease. Then only their torque is constant. So this is something always you have to keep in your mind. So these things always you have to keep in your mind. So as the voltage increases, current will decrease. Then only their torque is always equal to constant. Here also same thing. The torque is increasing means angular velocity will decrease. Here torque is decreasing means angular velocity will increase because the torque is always equal to constant. So you can see if T1 is greater than T2 means omega 1 is always less than omega 2. Suppose if N1 is equal to N2, then what is going to happen? Then always T1 is equal to T2 as well as omega 1 is equal to omega 2. So therefore, we can say if N1 is greater than N2 means T1 is greater than T2 and omega 1 is less than omega 2. If N1 is equal to N2, then T1 is equal to T2, theta 1 is also equal to theta 2. So you can get clearly from this equation. If N1 is equal to N2 means we can say T1 is equal to T2 as well as omega 2 is equal to omega 1. We can get this relation. So simple words I can say only one thing, which is torque and speed are always, we can say if one is increasing means the other will be decreased. If one is decreasing means other will increase. So these things always you have to keep in your mind. So with the help of gear, if the torque is increasing means speed will decrease. With the help of gear, if the torque is decreasing means speed will increase. So both cannot increase or both cannot decrease. If one is increasing means other will decrease. So this is the concept always you have to keep in your mind. So with the help of gears, if torque is increasing means speed will decrease. If torque is decreasing means speed will increase. So these things always you have to keep in your mind. We are going to discuss another concept which is called as the nodal method. See, in this nodal method, the basic principle is number of nodes is always equal to number of displacements. So we can say whatever the number of nodes is always equal to number of displacements. So basically, if you see clearly, suppose there is some
we can say some diagram is there. So if you want to convert from the given circuit into a representation, always we have to keep the number of nodes is always equal to number of displacements, and take an additional node which is a reference node. So you have to take an additional node which is basically a reference node, and connect the mass or inertia elements between the principal node and the reference always. So always you have to connect the mass or the inertia element between the principal node and the reference always, and connect the springs and the damping elements either between the principal nodes or between the principal node and the reference, depending upon the position. So always you have to connect the spring elements or the damping elements either between the principal nodes or between the principal nodes and the reference node, depending on the position. Whereas obtaining the nodal diagram and write the describing differential equation at each node. So you have to obtain the nodal diagram and you have to write the describing differential equations at each and every node. So basically this is called as the nodal method. So always you have to remember these are some of the important points in the nodal method, which is the number of nodes is always equal to number of displacements. So number of nodes is always equal to number of displacements. So take an additional node which is always a reference node. So connect the mass or the inertia elements between the principal node and the reference node always. Either you have to connect the spring elements as well as the damping elements either between the principal nodes or between the principal node and the reference node, depending upon the position. And we have to obtain the, so this is by this we are going to obtain the nodal diagram, and now we have to write the differential equations at each and every node. So basically we can say, suppose there is some complex diagram is there. Suppose a complex diagram is there, the diagram we can simplify with the help of this nodal method. So that complex diagram we can simplify with the help of this nodal method, and then we can write the equations for this analogous system. For this system we can write easily. So listen carefully. Suppose there is some complex diagram which is given in the question. So first we have to convert that complex diagram into the nodal method. Then this is a procedure. By this procedure we have to convert this complex diagram into this nodal method. So now we can write the at each and every node we can write the differential equation, and then we are going to get the overall differential equations for this complex system. Listen carefully. Suppose in the question they are given a very complex system. So with the help of this method we are going to draw the nodal diagram for that complex system. And now at each and every node, if you write the differential equation, then we are going to get some equations. Those equations are basically the differential equations of the other complex diagram. So this is a basic principle of this nodal method. So always remember, in the case of nodal method, the number of nodes is always equal to number of displacements. So number of nodes is always equal to number of displacements. And always take an additional node which is always a reference node. And always you have to connect the mass element or the inertia element between the principal node and the reference always. So always you have to connect the inertia or the mass element between the principal node and the reference node only. Whereas you have to connect the spring element or the damping element between the principal nodes or between the principal node and the reference node, depending on the position. First, so finally we are going to obtain a nodal diagram, and then we have to write the differential equations at each and every node. So finally I am going to repeat this one. Basically with the help of this nodal method we are going to convert a very complex diagram into a very simple diagram. So from this, if you are going to write the equation at each and every node, then we can obtain the equations in a very easier manner for this complex system, which is always you have to assume the number of nodes is always equal to number of displacements, and take an additional node which is a reference node. Always you have to connect the mass element or the inertia element between the principal node and the reference node always. And always you have to connect the spring elements or the damping elements either between the principal node or between the principal node and the reference node, depending on the position. And finally we are going to get the nodal diagram, and from this we have to write the differential equations at each and every node. So by this way we are going to get the diagram. So this is all about the nodal method. We are going to discuss the other concept which is called as the block diagrams. So basically, with this block diagrams concept, we are going to simplify a very complex diagram into a very simple diagram. So here, see carefully, here we have two blocks. The first block has a gain of G1 and the second block has a gain of G2. Suppose if the input is X, then what is the, here the output is nothing but X into G1. So here the output is X into G1. Here the gain is G2. Then what is the output here? Input into gain. X into G1 into G2 is equal to X into G1, G2. So now I want to basically simplify this block diagram into a very simple circuit, which is, it is a product of the G1, G2. So G1 and G2. Then what is going to happen? If the input is X, then what is the output? Output is nothing but, which is input into gain. So input is X, gain is G1, G2. So therefore we can say, this is the overall simplified block diagram. So whenever the two blocks are in series, the overall gain is the multiplication of the individual gain. So whenever the two blocks are connected in series, then the overall gain is the product of the individual gain. So G1 and G2. Then suppose here for this block diagram, see clearly, here these two are basically connected in a parallel fashion. Then what is going to happen? Here the input is X, so here also X, here also X. Then, so you see, here the output is X into G1. Here the output is X into G2. So here plus minus, here plus minus. So then what is going to happen? So you can see here plus minus. So you are going to get plus minus X into G1, plus minus X into G2. So this is the output. So if you take X common, then what you are going to get? Plus minus G1, plus minus G2. So this is what you are going to get. Then what is the simplified block diagram? So input is X and the overall gain is either plus minus G1, plus minus G2. So output is nothing but X into plus minus G1, plus minus G2. So in simple ways, I can say, if there is addition here, then whenever your two blocks are cut in parallel, just to the addition of these two gains. Suppose here it is a plus, it is a minus means, do the subtraction of G1 minus G2. Suppose here minus, here plus means minus G1 plus G2. Here both are minus means minus G1 minus G2. So this is what I am trying to tell you. So therefore we can say, so generally, whenever the two blocks are cut in parallel, their overall gain is the summation of the individual gains. So both are plus means plus G1 plus G2. If G1 here plus minus means plus G1 minus G2. Here minus plus means minus G1 plus G2. Both minus means minus G1 minus G2. So these things always you have to keep in your mind. Now for the next one. So for the next case, see there is a summer. There is a summer. Here plus minus is there. Here x1. Then what is the output here? The output is, summer is always going to either do a summation or subtraction. So here we are going to get x1 plus or minus x2 we are going to get. And the gain is G1. So what is the output? Output is nothing but x1 plus or minus x2 into G1. So this is the output that we are going to get. So now basically I want to basically take the summing point to the so I want to basically shift to the summing point from here to here. Then what is the changes I need to do? Listen carefully. So this is the summing point I have taken from input to output. So here the input is x1. Here the gain is G1. So what is the output here? Which is x into G1. So I keep the summing point here, plus minus. Then what is the change I need to do is basically here I have to include another gain, same gain G1. So same gain I have to include here also G1. And the input is now x2. See, so basically the input is x2. Then what is the output here? Which is x2 into G1. Then if I do the addition of these two things, then we are going to get x G1. So this is x1. Sorry, this is x1. So x1 G1 plus or minus x2 G1. So if you take G1 common, we are going to get x1 plus or minus x2 into G1. So this is the thing that you are going to get. In both the cases, we can say inputs are same and outputs are also same. So whenever you are going to shift the summer point from here to here, you have to include the same gain before the summer point also. So this is the concept regarding them. So basically in this block diagram, inputs are same and the outputs are same. Only the way that you are going to change the circuit diagram is going to get changed, but always the input and outputs are always same. So whenever you are going to keep the summing point after this output, after G1 means you have to include the same gain here also. Now for the another case, suppose here this is the circuit diagram they have given. Here the input is x1, here the gain is G1. So what is the output here? It is x1 into G1. So the output is here is x1 into G1. Here the input is x2. Here there is summing point plus minus. But then what is the overall output? It is x1 g1 plus or minus x2 is the overall output. Suppose if I want to shift this summing point from output to input, then what is the changes I need to do? So same circuit diagram. Here the input is x1. Here the output is, so here the input is x2. Summing point I have taken here. Then what is the extra thing that I have to multiply, which is 1 by g1. I have to keep here 1 by g1. I have to include here. Then we will see what is the output that you are going to get. Is it same as the previous one or not? We will see here. So what is the output here? Which is x2 by g2. x2 by g1. x2 by g1, right? Here what is the overall input? x1 plus or minus x2 by g1. Then the gain is g1. So what is the output? Input into gain. So you are going to get x1 plus or minus x2 by g1 into g1. Then if you simplify, what you are going to get? x1 g1 plus or minus x2. So g1 cancels, so you are going to get x2. So now you can see here both the outputs are same. So inputs are same, outputs are same. So you are going to get. So this is the way. So whenever you are going to shift the summing point from output to input, then you have to include a gain of 1 by g1, the reciprocal of this gain. So this is the thing always you have to keep in your mind. So now for the next circuit, so here the input is x, here there is a gain. So here we are taking basically we are taking output sampling. So here x means here also x. Then what is the output here? Which is x into g1, which is equal to x into g1 or g1x. Suppose if I want to take this one from here to here, if I want to take the sampling from output, then what is the change I need to, I have to do? What is the change I have to do? So always the inputs and outputs are same. So this is x, then this is again g1. So here it is again g1 into x. So if I take the sampling from here, then what is the change? Basically I need only x only here. So what is the extra thing that I have to keep here? So here it is basically g1 into x. So if you multiply 1 by g1 with g1x, then what you are going to get? Finally x you are going to get. So you can see whenever you are taking the sampling from input to output, then you have to keep a gain of 1 by g1. Then the output you are going to get same as the previous case. So in both the circuits, inputs are same and the outputs are same. So these things always you have to keep in your mind. So for this circuit, so if you see clearly here, there is some circuit. If the input is x, so if the output is x into g1. So we are taking the sampling from here only. So this is also x into g1. So then whatever changes I need to do if I take the sampling from output to input. Suppose if I do the sampling from input, then what are the changes I need to do? So here x, here also g1, so output is there x into g1. So if I shift the sampling from here to here, I want to get the still output as x into g1 only, then I have to keep an extra block of gain g1. If the input is x, so here the input is still x. So x into g1 is nothing but again x into g1. So therefore, this is a thing always you have to keep in your mind. So therefore, inputs are same, outputs are still the same. So basically this block diagram is both the circuits. See the simplified circuit is somewhat simpler, but the overall resultant value is same. What the inputs, the outputs are same. Just by doing some modifications, still we have to get the same inputs and same outputs. Now for this one, so you can see clearly here for this block diagram, which is R, if the input is R, then the output is C. Here the gain is G, here the gain is H. So the feedback gain is H and the plant gain is G, here plus minus. So what is the equivalent circuit diagram? So equivalent block diagram, which is G by 1 minus plus G into H. So input is R and output is C. So if it is the plus means use here minus. If it is minus means use here plus. So this formula always you have to keep in your mind, which is G by 1 minus plus G into H. Here plus means you have to keep here minus. If it is a minus means you have to keep here plus. So this one always you have to keep in your mind. So you can write this block diagram in the other fashion also. In the other fashion also you can write, which is, listen carefully, you can write it in the other fashion also. Still you are going to get the same result. Suppose for this one, what is the gain? What is the overall gain? Which is nothing but for this system, what is the overall gain? So G into H by, you can say here 1 minus plus G into H into 1 plus the gain is 1. So you are going to get like this. And if you multiply by 1 by H, because these two are in series, so overall gain is the product of the individual gains. Then what you are going to get? H cancels. So you are going to get the overall gain, which is equal to G by 1 minus plus G into H. So same as the previous case. So this is also equal to same gain. So these three circuits are equal. This is that we can say the equal way of representing. So always remember, which is G by 1 minus plus GH. Here plus means here minus means here plus. Both are vice versa. So these things always you have to keep in your mind. So now for the another thing, suppose there is a summer point here, there is a summer point here. So if the input is an x, here the input is y, plus or minus. Then what is happened here? So here the output is x plus or minus y. Here there is another summer point, which is plus minus. Then what is the overall output? X plus or minus y plus or minus z. So this is the we can say overall input and overall output that we are going to get. Suppose if I shift the summing point, this summing point I am shifting here and this summing point I am shifting here. This summing point I am shifting here and this summing point I am shifting here. Then what is the output and input? We will see what is going to happen. So input is x. Here the summing point I shifted here. So I am going to take z. So here what is the output you are going to get? Which is x plus or minus x plus or minus z. This summing point I have shifted here. Then what is the here? Y. So again if you add this one, we are going to get x plus or minus z plus or minus y. This is again equal to x plus or minus y plus or minus z. So therefore, whenever you are going to shift the two summing points, if there is nothing is present between them, then you don't have to do any modifications because still you are going to get the same result. So whenever you are going to shift the two summing points, between them, if there is nothing is present, still the output is same. You don't have to do any modifications because both are going to give you the same output. Suppose for the other case, so you can see this is the circuit diagram they have given. Suppose there is summer point, their input is x, their input is y. Then what is the overall output? X plus or minus y. Here the sampling is x. Suppose I can represent the circuit in the other fashion also. How is like this? So here there is a summer point. Here the input is x. Here the input is y plus or minus. So the output is x plus or minus y. Suppose if I take another sampling point, if I take another summing point, so here also y. So if you're adding these two elements and I'm taking the output from here, then if you add these two things, what you are going to get? X plus or minus y minus plus y. Then what is it? Y by cancels. Then you are going to get the output as x. So the summing point, suppose this one, if I want to take from another summing point, then like this, with the x plus or minus y, here reverse, you need to do the reverse addition. Here plus y means here minus y, here minus y means here plus y. Then overall value you are going to get here, the output is x. Here is x, here is x, here is plus or minus y, here is x, here is plus or minus y, here is also x. So always the circuit is always going to give you the same output. So now for this circuit, if you see, this is summer point. If the input is x, if the input is y. So output is x plus or minus y because of summing point. Here I am taking the output. So the output is also same as this one, it is x plus or minus y. Suppose what I will do for the same circuit, suppose if I add a new summer point, and if I want to take this, if I want to take this output from the input, then what is the changes I want to do? So if I want to take this sampling from input, then what is the extra changes I want to do? So therefore, you have to take the another summing point and you have to add this value by here also. The input is x, their input is plus or minus y. So overall output is x plus or minus y. Here the input is x and input is plus or minus y. So output is x plus or minus y. In the both ways we are going to get. So whenever you want to take the sampling from output to input, you have to add a new summer point with the same plus or minus y. But if you want to take the sampling from input to output, here you have to add the reverse summing point. Here plus or minus y means here minus plus y. Then you are going to get the same result. So these are the different circuits that you can see in the block diagram. So basically, with the help of block diagram, we are going to convert a very complex circuit into a very simple circuit. Always the inputs are same, the outputs are same. Only the modifications we have to do in order to get the same result. So always the simplified circuit is very simple when compared to the complex circuit. So this is all about the block diagrams. Now we are going to discuss another concept which is called as the Mason's gain formula. So with the help of Mason's gain formula, suppose if there is any complex block diagram, we can convert the complex block diagram into a basically. So basically, if there is any complex diagram, then we can obtain the transfer function very easily with the help of this Mason's gain formula. Irrespective of the complex nature of the diagram, we can simply get the transfer function. We can easily get the transfer function for the complex diagram with the help of this Mason's gain formula. So by this method, we can get the transfer function of any complex block diagram in a very simple manner. That is the basic agenda of this Mason's gain formula. So the transfer function, which is the Laplace transform of output by the Laplace transform of input, assuming the initial conditions are 0, which is the transfer function formula is equal to sigma pk into delta k by delta. So this formula always you have to keep in your mind. So transfer function is the ratio of the Laplace transform of output by the Laplace transform of input, which is equal to sigma pk delta k by delta, where pk is called as the path gain of the kth forward path. So the path gain of the kth forward path. So basically, what is the path here? Path means always you have to travel from the initial point to the final point. You have to always travel in the direction of the arrows. So whenever you're traveling from initial point to the final point in the direction of arrows without traveling any node more than once, that is called as a forward path. So whatever the gains which are included in that path, always you have to multiply. Then you are going to get the overall forward path gain, which is pk is the path gain of the kth forward path. What is the delta? Delta is nothing but which is equal to 1 minus sum of gains of all individual loops plus the sum of gains of the product of two non-touching loops minus sum of gain of product of three non-touching loops and goes on. So this is the value of delta, always plus minus plus minus plus minus. So delta is equal to 1 minus sum of gains of all individual loops plus sum of gains of product of two non-touching loops minus sum of gains of product of three non-touching loops, and it goes on always plus minus plus minus. So then what is the delta k? Delta k is nothing but the value of delta which is obtained by removing all the loops which are touching the kth forward path or keep the loops as 0. So basically, what is the meaning of delta k? See, from this delta, whichever the loops that are touching that forward path, so whichever the loops which are touching that forward path, then all those loops we have to remove or assume. Currently, you have to assume all those loop gains are 0. Then the resultant value that we are going to get from delta, that is called as the delta k. So this is the point always you have to keep in your mind. So remember, which is so therefore, so basically here we can say whichever the loops which are touching that means the kth forward path, that loops we need to keep them as 0 in this one delta. Then the resultant value that you are going to get is called as the delta k. So the value of delta which is obtained by removing all the loops which are going to touch the kth forward path or keep that loops as 0 in the value of delta, then the resulting value that you are going to get is called as the delta k. So this one always you have to keep in your mind. So always remember. So what is the meaning of path means? I have already told you. Path means whenever you are traveling from initial point to final point in the direction of arrows without traveling any node more than once is called as the we can say the forward path. And what is a loop? Loop means the initial point is equal to final point, and you have to always travel direction of the arrows without traveling any node more than once. So this is you can easily know about the loops. This is all about the loops and paths. So loop gain is nothing but whichever the just multiply all the gains which are present in that loop, that is called as a loop gain. So always remember a transfer function by using the Mason's gain formula is equal to sigma pk delta k by delta. Where pk is called as the path gain of the kth forward path, and delta is nothing but 1 minus sum of gains of the individual loops plus sum of gains of the product of two non-touching loops minus sum of gains of the product of three non-touching loops, and goes on. And delta k is nothing but whatever the value of delta, the value of delta which is obtained by removing all the gains, all the loops which are going to touch that kth forward path or keep that loop which are going to touch that kth forward path as 0. And the resulting value that you are going to obtain from delta is called as the delta k. So this is all about the Mason's gain formula. So we can easily get the transfer function of any diagram in a very fraction of seconds with the help of this Mason's gain formula. Always you have to remember this formula in order to solve the questions in a very fraction of seconds. So this is plus minus plus minus plus minus. So finally I can say Mason's gain formula is that basically we can get the transfer function of any complex diagram in a very fraction of seconds with the help of this Mason's gain formula. And the transfer function is equal to sigma pk delta k by delta, where pk is called as the path gain of the kth forward path, and delta is nothing but 1 minus sum of gains of all individual loops plus sum of gains of product of two non-touching loops minus sum of gains of product of three non-touching loops, and goes on. So plus minus plus minus plus minus. And delta k is nothing but the value of delta which is obtained by removing all the loops which are touching the kth forward path, or the value of delta which is obtained by keeping all those loops which are touching the kth forward path as 0. That is called as the delta k. So path means you have to travel from initial position to final position in the direction of arrows without traveling any node more than once. And the value of loop is nothing but the initial point is equal to final position, and you have to always travel in the direction of arrows without traveling any node more than once. So these things always you have to keep in your mind. So this is all about the Mason's gain formula. So now the next concept is here the transfer function for the servo motors. So basically now we are going to learn about the another concept which is called as the transfer function for the servo motors. So what is the transfer function for the servo motors? So this is the concept that we are going to learn. So I have already told you for servo motors, servo motors are nothing but these are basically like synchronous motors, I can say, in a simple fashion. So for the servo motor, I have already told you the stator has 3-phase winding and the rotor has single-phase winding. So this point always you have to keep in your mind, which is servo motors. For servo motors, the stator has 3-phase winding and the rotor has single-phase winding. So this concept always you have to keep in your mind. So for a servo motor, the stator has 3-phase winding and the rotor has single-phase winding, same as the synchronous motor, I can say like that. So now, servo motors, it is a AC or DC motors in the control systems. So these are basically AC as well as the DC motors which are used in the control systems. And the servo motors are basically classified into two types. They are DC servo motor as well as the AC servo motor. So basically we can say servo motors, they can be used as the AC servo motors as well as the DC servo motors in the case of the control systems. So servo motors are basically, they are used in the control system in a very large applications. They can be used for the AC application as well as the DC application. So therefore we can say servo motors, for servo motors, stator has single phase winding and the rotor has the stator has 3-phase winding and the rotor has single phase winding. And servo motors are basically classified into two types in the case of control systems, which are AC servo motor as well as the DC servo motor. So we can say in simple words like this: servo motors are basically in stator it has 3-phase winding and the rotor it has single phase winding. So basically these are classified into two types in the case of control systems, which are DC servo motor as well as the AC servo motor. So now we will see what is the transfer function of the armature control DC servo motor. So now we are going to get the transfer function of the armature control DC servo motor. So this is we are going to get the transfer function of the armature control DC servo motor. So you can see this is the armature and this is the field. So this is the armature circuit and this is the field circuit. So for the armature, we are going to give the voltage, which is armature voltage is EA, supply voltage is EA, and RA is the armature resistance, and this is the motor. So motor has the back EMF EV, and the current is armature current is IA. So basically, for this motor, we are going to connect some load. So load will have some inertia J and also some damping coefficient B. So J is the inertia and B is the damping coefficient. So Tm is nothing but it is a motor torque. This is the amount of torque that is produced by this motor, which is Tm. So this is a field winding. So this is a field winding means it will have some resistance RF and it will have some inductance LF. And it's a field voltage is EF and the field current is IF. So now we are going to obtain the transfer function for this armature control DC servo motor. From the armature, we are going to vary the voltage. So the input is the voltage and the output is the speed of angular displacement. Anything is the, you can say it is the output. So now we are going to see what is the transfer function of this we are going to get. The input is armature voltage and the output is angular velocity or angular displacement. Anything is the output. So between these two things, we are going to get the transfer function is output by input. The Laplace transform of output by the Laplace transform of input. So output can be either angular velocity or angular displacement, and the input is armature voltage. So theta of S by EA of S is the basic transfer function we want to obtain by this circuit diagram. So you can see flux is always directly proportional to field current. So flux is always directly proportional to field current. So flux is always directly proportional to field current. So if you want to remove the proportionality constant, you have to keep some constant. So phi is equal to Kf into If. So this is the first equation. Then the motor torque is always directly proportional to flux into armature current. In the case of DC motor, I've already told you the torque is always directly proportional to flux into armature current in the case of DC motor. So torque means here motor torque. So Tm is directly proportional to flux into armature current. So you know what is the flux value, you know, which is Kf into If. Just now we have seen. This is nothing but Kf into If. Same thing I have substituted, meaning everything is same. So I want to remove this proportional to constant. So I have to keep another constant, which is equal to K1. I am going to keep here. So Tm is equal to K1 into Kf into If into Ia. So I am going to assume K1 into Kf is nothing but Kt. I am going to assume. So Kt is the overall constant. So Tm is equal to Kt into Ia. So this is another equation. So this is basically a time domain. Suppose if I want to get in the Laplace domain, then Tm of S is equal to Kt into I of S. So this is in terms of Laplace domain, and this is in terms of time domain. Suppose if I am going to apply the KVL in this loop, the time domain, then I am going to get Ea is equal to Ia into Ra plus Eb. So this is in the time domain. So if I apply the Laplace transform, then I am going to get E of S is equal to Ra into I of S plus Eb of S. So this is the equation that we are going to use, which is E of S is equal to Eb of S plus I of S into Ra. So this is another equation that we are going to get. And you know, basically this back EMF is always directly proportional to the rate. It is always directly proportional to angular velocity. So Eb is always, the back EMF is always directly proportional to angular velocity, which is Eb is directly proportional to angular velocity, means the rate of change of displacement, angular displacement. So Eb is directly proportional to deta by dt. So if I want to remove the proportional constant, I have to keep a constant as Kb. So Eb is equal to Kb into deta by dt. So now, basically, suppose this is in terms of time domain. Suppose if I apply the Laplace domain, then I am going to get Kv of S is equal to Kb into Sc into theta of S. So this is in the case of the Laplace domain. So back EMF is always directly proportional to angular velocity. Angular velocity means the rate of change of angular displacement. So Eb is directly proportional to deta by dt. So if you want to remove the proportional constant, keep the value of Kb. So this is in the time domain. So by applying the Laplace domain, then we are going to get Ab of S is equal to Kbs into theta of S. Then you know what is the overall torque. The motor torque we can write in terms of this value. Just now I have seen the different types of equations. So Tm is equal to J into d square theta by dt square plus B into theta by dt. So just now we have discussed the motor torque is equal to J into we can say J into d omega by dt plus B into omega. Omega is equal to d theta by dt. So in this fashion, if you write, we are going to get Tm is equal to J into d square theta by dt square plus B into d theta by dt. So if you apply the Laplace domain for this equation, then we are going to get Tm of S is equal to, then we are going to get J into S square into J into theta of S plus SB into theta of S. So if we take theta of S common, then we are going to get J into S square plus B into S. So this is the equation that we are going to get. This Tm of S is equal to theta of S into J into S square plus B into S. So this is the equations that we are going to get. So now basically with the above these equations, I want to draw the overall block diagram. I want to write it like this. So this is the block diagram that you are going to get. So this is the block diagram that you are going to get with the help of all these equations. The input is A of S and the output is theta of S. The input is armature voltage and the output is angular displacement, which is theta. So the Laplace domain is A of S and theta of S. So now you will see the block diagram. So what is the here equation? This is the equation. What is the equation here? Which is basically, this is the back EMF. So E of S minus ED of S. So you are going to get E of S minus ED of S. Here this is nothing but basically I of S. So I of S is nothing but I of S. So you can see clearly IA of S is equal to E of S minus EB of S by RA. Same thing we have got E of S minus EB of S by RA is nothing but IA. Then what is the motor torque? Motor torque is equal to Tm of S is equal to Kt into I of S. So here Kt and this is Tm of S. Then what is here equation? Tm of S is nothing but, then you can see this is theta of S. So what is theta of S? Theta of S is equal to Tm of S by J into S square plus Vs. So therefore theta of S is equal to Tm of S into by into 1 by j into s square plus b into s. So this is the theta of s you are going to get. And what is EB of s? EB of s is equal to kds into theta of s. This is kb into s or s into kb. So EB of s is equal to s into kb into theta of s. So this is the overall thing that we are going to get. So you can see clearly this is the I of s is equal to E of s minus EB of s by RA, and Tm of s is equal to KT into I of s, and theta of s is equal to Tm of s by j into s square plus b into s, and EB of s is equal to s into kb into theta of s. So with the help of these equations, we have drawn this block diagram. So this is the, we can see there is a closed loop. So there is a closed loop is there in this circuit. In the case of armature control, this there is a closed loop is there in this circuit. Now, if you obtain the theta of s by E of s with the help of Mason's gain formula, if you try to obtain the theta of s by E of s, finally we are going to get the transfer function in this format, which is k dash by f by s into j by f into s plus 1. So this is the equation that we are going to get in the final format. So we can write like this: in k dash by f, I will write this k by s into this j by f, I will write as a tau or t. So ts plus 1. So this is the final representation of this block diagram. Theta of s by E of s is equal to k by s into ts plus 1. So what is the order? What is the order means? Here the highest power is s square. So the order of the system is 2. So one pole at 0 and the other pole as minus 1 by t. There are no zeros. So you can see what is the order of the system, which is 2. It has one pole at origin and the other pole at minus 1 by t. And there is no zeros. So k is called as a gate and t is called as the time constant. So then what, see k dash we are going to assume is equal to kt by Ra, and the value of f is nothing but b plus kt into kb by Ra, and this k is nothing but k dash by f, and t is nothing but j by f. So these things always you have to remember. So I have assumed which is k dash is equal to kt by Ra and f is equal to b plus kt into kb by Ra. Then I have assumed k is nothing but k dash by f and t is nothing but j by f. So t is called time constant and k is called as the gain. So this is the overall transfer function of this armature control DC servo motor. The output is theta of s and the input is EA of s. So basically it is a second order with a one pole at 0 and the other pole at minus 1 by t, and the gain is k and there is no zeros. So this is all about the transfer function of the armature control DC servo motor. Means input is armature voltage, which is EA, and the output is the angular displacement. So this is all about the transfer function of the armature control DC servo motor. So now the next concept is the transfer function of the field control DC servo motor. Means now here the input variation is the field voltage, means EF of s. Then the output is theta. Then I want to find what is the transfer function between this one. In the previous case, with the help of armature voltage, we are going to control the theta. But now, in this case, with the help of field voltage, which is EF of s, we are going to control the angular displacement. Then what is the relation I want to figure out? So the input is nothing but here field voltage, and what is the output, which is equal to theta. So input is equal to EF and the output is equal to theta. So we know all this equation just now. With the help of those equations only, now we have to obtain the block diagram. Same thing, flux is directly proportional to field current. So if you want to remove the proportionality constant, keep the value of Kf. So phi is equal to Kf into If. Just now we have seen. And the motor torque is directly proportional to flux into armature current. So flux is nothing but Kf into If. So if you want to remove the proportionality constant, keep the constant as K1. Just now we have seen. And Kf into K1 into Kf is nothing but which is equal to Kt. So Kt. And here, if you see clearly, this If is a variable. Why If is a variable? Because EF is a variable. If EF is a variable, If is also variable. But as the EA is a constant, then IA is also constant. So therefore, this also I am going to assume as a constant. Then I am going to assume K into Kf into IA is nothing but I am going to assume its value is equal to Kt. So this value I am going to assume is equal to Kt. This value I have assumed as a Kt. And the remaining only variable is If. So only variable is here If. So this is the If here. Then if this is in the terms of time domain, so if you want in the terms of Laplace domain, we are going to get Tm of s is equal to Kt into, so Kt into KT into IF of S. Then you know what is a KVL in a field circuit. In a field circuit, if you write the KVL in a field circuit, then EF of T is equal to IF of T into RF plus LF into dIF of T by dt. Because of the resistor and there is an inductor of field resistor of RF and the inductance and the field inductance is LF. So by this equation we are going to get. So if we apply the Laplace domain, then we are going to get EF of S is equal to IF of S into, we are going to get IF of S into RF plus S into LF into IF of S. So if we take IF of S common, then we are going to get RF plus S into LF. So EF of S is equal to IF of S into RF plus S into LF. Then we already know back EMF is directly proportional to rate of change of angular displacement. Or we can say the back EMF is directly proportional to angular velocity. So angular velocity it is directly proportional to rate of is equal to the rate of change of angular displacement. So therefore EB is directly proportional to d theta by dt. So if we remove the proportional constant, we are going to get its value is equal to kb. So AB is equal to kb into d theta by dt. If you apply the Laplace domain, we are going to get EB of S is equal to K S into kb into a theta of S. Then you know all these equations, you know Tm of S also. So you know Tm is nothing but J into d square theta by dt square plus B into d theta by dt. Just now you have seen. So if you apply the Laplace domain, we are going to get Tm of S is equal to theta of S into J into S square plus Vs. So now you know all these equations. So now all these equations. With the help of these equations, now we are going to draw the block diagram. So this block diagram is same as the previous one. It is same as the previous one. So here see clearly. So here the input is now EF of S. So what is the current IF of S? So F of is nothing but EF of S by RF plus S into LF. So IF is nothing but EF of S by RF plus S into LF. And Tm of S is nothing but KT into IF of S. Just now we have seen. So Tm of S is equal to KT into IF of S. And theta of S is nothing but Tm of S by J into S square plus B into S. And you know EB of S. So basically you don't need EB of S. Practically, if the input is EF and output is theta, you don't need any EB. You don't need any EB also, because in the circuit, what is the input is EF and output is theta. So only these three are enough. You don't have to draw this one, but I have drawn for the just for learning purpose. So EB of S is nothing but S into KB into theta of S. So actually this is we don't need actually, because the input is F of S and the output is theta of S. So practical I can speak. We don't need this branch. We don't need only this branch. Only up to here is sufficient. So if you see clearly, there is no feedback. There is no feedback from output to input. So in the case of armature control, yes, there is a feedback from output to input. Whereas in the case of field control, there is no feedback from output to input. So these things always you have to keep in your mind. So always remember. So always remember this point. So always you have to remember this important point. So if you want to know what is the transfer function, so what is the transfer function is just to the multiplication of all these three quantities. So here I am going to write here theta of S by EF of S. So what is the overall gain? Overall gain is just multiply all these things, which is 1 by RF plus S into LF into KT into 1 by J into S square plus Vs. So if you multiply all these things, we are going to get the overall transfer function. So by seeing this, I can say like this, which is here the order is 1, here the order is 2. So overall order will become 3. So this system has a total order of 3. It has a total order of 3. And if you multiply, you are going to get the KT by RF plus S into LF into J into S square plus Vs. So we can say the overall order of the system is 3. Whereas the previous case order is only 1. Order is 2. So for the previous case, the order is 2. But here the order is 3. So these things always you have to keep in your mind. So finally I can say, in the case of armature control this servo motor, yes, there is a feedback from output to input and the order of the system is equal to 2. Whereas in the case of field control this servo motor, there is no feedback from output to input and the order of the system is nothing but which is equal to 3. So these things always you have to keep in your mind. We are going to discuss another concept which is called as the AC servo motor. AC servo motor. So basically, we are seeing clearly in this picture. So they are given two windings. One is the control winding and the other is called as the reference winding. So for this control winding, the voltage is EC and for reference winding, the voltage is ER. So we can say, so EC is the control voltage and here is the reference voltage. Here there is a rotor. So for this rotor, we are going to connect a load. So the load will have the moment of inertia and the damping constant. So this the load is AC motor. It is going to provide some torque. It is going to provide some torque. Torque is a Tm. So because of this torque, it will have some rotation theta as well as angular velocity omega. So now, if you are going to draw the torque versus speed characteristics for this AC servo motor, so we are going to get like this. So this is this red line. This red line is nothing but it is a graph between the torque and the speed characteristics of this AC servo motor. Whereas this bigger one is called as the torque speed characteristics of the induction motor. So these things always you have to keep in your mind. So this is the graph. This is the graph of the torque speed characteristics of the two-phase induction motor. Whereas this is the graph between the torque speed characteristics of the AC servo motor. So you can see this blue one is the graph between the torque speed characteristics of the two-phase induction motor. For this two-phase induction motor, always the X by R ratio is always larger. Shortcut to remember is it is having bigger size. So X by R ratio is also very large. Whereas this is the graph between the torque speed characteristics of the AC servo motor and its X by R ratio is very, very small. So big means bigger size, less means lesser size. Shortcut to remember. So for this two-phase induction motor, this is the torque speed characteristics and its X by R ratio is very larger. And this is the graph between the torque speed characteristics of the AC servo motor and its X by R ratio is very small. So these things always you have to keep in your mind. So now here is called as the constant voltage. Here is always a reference voltage. Always we are going to make it constant. And AC is called as a changing voltage as per the requirement. So always we will try to make here as the constant and AC always will change as per the requirement. So AC is for the reference voltage. Always we are going to keep it as a constant voltage and AC is a variable voltage. We are going to change this voltage as per the requirement. So whatever this rotor is basically a squirrel cage. So whatever this rotor we are going to use in a servo motor, it is basically a squirrel cage rotor and it has the low inertia and the high starting torque. So it has low inertia and it has high starting torque and also it has the large length as well as small diameter. So length is large and diameter is small means L by D is very, very large because length is large and diameter is small means the ratio is always large. And its rotor has the high resistance. So because of this only X by R ratio is small because as the resistance is very high, so X by R ratio is very, very less in the case of AC servo motor. So basically, in the case of AC servo motor, the rotor is basically a squirrel cage rotor. It has low inertia. And it has high starting torque. You can see clearly at the speed is equal to 0. At the speed is equal to 0, we have a non-zero torque. It is a starting torque. So it is a self-starting motor. It's a self-starting motor because at speed is equal to 0, it has non-zero torque. So this self-starting torque, it is a self-starting motor and it has high starting torque. And its length and it has large length and small diameter. So its length is large, the diameter is small. So therefore, the L by D ratio is also large. And its rotor has the high resistance. So basically, its rotor has high resistance. So because of this only, the X by R ratio is very small. So these are the specifications of this rotor which is going to be used in this AC servo motor. So what are the specifications of the rotor which is used in AC servo motor is basically a squirrel cage rotor. It has low inertia and it has high starting torque. It has large length and small diameter. So because of this reason, the L by D ratio is very larger and its rotor resistance is also very high. So because of this, the X by R ratio is very smaller. So now the motor torque is always directly proportional to the control voltage. The motor torque is always directly proportional to control voltage. So if you want to remove the proportional to constant, you have to use a constant is Km. So Km is equal to Km into AC. So I already told you in the case of AC servo motor, what is the torque Km is directly proportional to control voltage. So therefore we can say that Km is directly proportional to AC. So if you want to remove the proportional to constant, then use a constant Km, which is Km is equal to Km into AC. So this is in the time domain. So if you want to apply the Laplace domain, then you are going to get Tm of S is equal to Km into EC of S. So this is the Laplace domain equation with respect to input as well as the Tm of S and E of EC of S. Then what is Km? Km is nothing but it is the ratio of the T0 by EC. So Km is nothing but it is the ratio of Tm by EC. Tm is nothing but T0 we are going to assume. So now Tm is nothing but, Tm is nothing but, this motor torque is nothing but J into d omega by dt plus v into omega. So this is general expression we know. So apply the Laplace domain, Laplace transform, then we are going to get Tm of s is equal to s into j into omega of s plus b into omega of s. So if we take omega of s common, we are going to get Tm of s is equal to omega of s into js plus b. So now we are going to equate these two equations because Km of s is common. Then we are going to get Km into Ec of s is equal to omega of s into js plus b. So if we do the ratio omega of s by Ec of s, omega of s by Ec of s is nothing but Km by js plus b. So if you see clearly, the output is the angular velocity and the input is the control voltage. So this is the transfer function with respect to output and the input. The output is angular velocity and the input is control voltage. So omega of s by Ec of s is equal to Km by js plus b. So this is the equation that we are going to get. So we can say it is a first order system. So without any correction factor. So this is the equation without any correction factor. Suppose if you want to use the correction factor, then we will get omega of s by Ec of s is equal to Km by js plus b minus n. B minus n. So this is the, yes, you have to subtract a small value m from this p. This is with correction factor. Where T0, this unit is called as a starting torque. Km is nothing but is a ratio of the starting torque by control voltage. So T0 is called as a starting torque and m is called as a correction factor. P is basically the slope of the speed torque characteristics. So m is nothing but it is a slope of the speed torque characteristics. So this is the transfer function without any correction factor, and this is a transfer function with a correction factor. Where T0 is called as the starting torque and m is called the correction factor. It is basically the slope of the speed torque characteristics of this AC servo motor. So basically, I already told you, servo motors are basically two types, DC servo motor and AC servo motor. In the previous case, we have studied the DC servo motor with the armature voltage control as well as the fuel voltage control. Now in the AC servo motor also we have studied. So this is the transfer function of the AC servo motor. All these things we have discussed. So we can say, what is AC servo motor? The order is the 1. The order is the 1. So you can see clearly from here. And always it's a ratio, X bar ratio is always lesser because the resistance is very, very more. So these things always you have to keep in your mind. So this is all about the AC servo motor. And we are going to discuss about the other concept which is called as the time response analysis. So this is about the time response analysis. So whenever I am going to draw the graph between the output with respect to time. So output is a y of t. I am going to draw the graph output with respect to time. So this is the graph I am going to get. So this is the graph I am going to get here. So this is called as the, so this is the desired output. So this is the desired output, but this is the actual output. So this is the desired output that we want, but this is the actual output that we are going to get with respect to time. So finally you can see there is some steady state error. You can see clearly there is a somewhat steady state error between the desired output as well as the actual output that you are going to get. So whatever the input is nothing but I want this input itself as the output. So I want this input itself as the output. So this is the input, or we can say desired output also we can say, because input itself is the desired output and this is the actual output that we are going to get. So finally I can say there is somewhat steady state error between the actual output with actual output as well as the desired output of input. So this is called as the transient state and this is called as steady state. So this is called as the transient state and this is called as the steady state. So whatever the study of transient state is called the transient state analysis, and whatever the study of the steady state is called as the steady state analysis. So these things always you have to keep in your mind. So whatever the study of the transient state is called as the transient state analysis, and whatever the study of the steady state is called as the steady state analysis. So always we want the actual output to become the desired output, but practically there is somewhat error between the actual output as well as the desired output. That is called as a steady state error. So always there is a somewhat steady state error between the actual output as well as the desired output. Desired output is also called as the input because always the input itself is the desired output that we require. So this is all about the time response analysis. So now we will discuss another concept which is called as a type as well as the order. So the definition of type and order we have to learn clearly. So basically type is nothing but So in the open loop transfer function g of h of s, the number of poles which are going to present at the origin is called as the type of the system, and order is nothing but and the order means in the characteristic equation 1 plus g of h of s, the highest order is called as the order of the system. So always this things always you have to keep in your mind. Listen carefully. Type means in the open loop transfer function g of h of s, the number of poles which are going to present at the origin is called as the type of the system, and order remains in the characteristic equation 1 plus g of h of s is equal to 0. In the characteristic equation, the highest power is called as the order of the system. So these two definitions always you have to keep in your mind. So finally I can say type. Type means here, finally I can say in the open loop transfer function g of h of s, the number of poles which are going to present at the origin is for the type of the system, and the order means in the characteristic equation 1 plus g of h of s is equal to 0, the highest power is called as the order of the system. So you can see clearly this is the open loop transfer function which is g of h of s, and the standard format is k into 1 plus t0s and goes on as the power of p into 1 plus t1s and goes on. So this is the standard format of the open loop transfer function. So I already told you the number of poles which are going in the open loop transfer function g of h of s, the number of poles which are going to present at the origin is called as the type of the system. So this is p is called as a, so this p is called the type of the system. If p is equal to 0, then we can say it's a type 0 control system. If p is equal to 1, we say it's a type 1 control system. If p is equal to 2, then we say it is a type 2 control system. If p is equal to n, then we say it is a type n control system. So always k is called as a zero frequency gain, and is also called as a DC gain. So this is a k is called as a zero frequency gain, but is also called as a DC gain. Means whenever the frequency is equal to 0, then the gain which is going to present in the system is called as the k. It is only k is going to present. Only k is going to present. So therefore k is called as the zero frequency gain or DC gain. Means whenever the frequency is equal to 0, then the gain which is going to provide by the system, that is called as the zero frequency gain or the DC gain. Means when the frequency is equal to 0, then the overall gain produced by the system itself is called as the DC gain or the zero frequency gain. So always remember, which is where p as the power of p means if p is equal to 0, then we can say the type 0 control system, and p is equal to 1 means we say it's a type 1 control system. If p is equal to 2 means it's a type 2 control system, and if p is equal to n means it is called a type n control system, and k is called as a zero frequency gain or the DC gain. So this is the all about the type. Type means we can say for the open loop transfer function g of h of s, the number of poles which are going to present at the origin is called as the type. It is called type of the control system. So I've already told you for the closed loop transfer function c of s by r of s, the default for the negative feedback system which is equal to g of s by 1 plus g of s h of s. So this is the closed loop transfer function. We can say c of s by r of s is equal to g of s by 1 plus g of h of s. So this is the overall transfer function of the negative feedback. So always we can say this is the transfer function of the negative feedback system. Always we are going to choose the negative feedback system, and it's a closed loop transfer function which is c of s by r of s is equal to m of s is equal to g of s by 1 plus g of h of s. So this is called the characteristic equation. So for the overall transfer function, the denominator part is called the characteristic equation. So the characteristic equation is equal to 1 plus g of h of s is equal to 0. If we equal to 0, the highest power is called as the order of the system. So this point always you have to keep in your mind. So therefore we can say finally I can say only one thing I can say, which is, so type means in the open loop transfer function g of h of s, the number of poles which are going to present at the origin is called as the type of the system, and in the characteristic equation 1 plus g of h of s is equal to 0, the highest power is called as the order of the system. So these two definitions always you have to keep in your mind. So let me discuss some more important points, which is the steady state response analysis depends on the type of the control system, and it is the number of open loop poles occurring at origin. So I've already told you, whatever the steady state response analysis is always going to depend upon the type of the control system, and it is the number of open loop poles which are going to occurring at the origin. Whereas the transfer state analysis depends upon the order of the control system, and it is the highest power of the S in the characteristic equation. So I've already told you basically what the type of the control system is. In the open loop transfer function g of h of s, the number of poles which are going to present at the origin is called type of the system, and the steady state analysis is always going to depend upon the type of the system. Whereas the highest power in the characteristic equation, the highest power of S is called as the order of the system, and the transient state analysis is going to depend upon the order of the system. So these things I've already told you so many number of times. So always remember, the steady state analysis is always going to depend upon the type of the system, whereas the transient state analysis is always going to depend upon the order of the system. So here I'm going to write here an important point. Steady state analysis is always going to depend upon the type of the control system, whereas the transient state analysis is always going to depend upon the order of the control system. So these two definitions always you have to keep in your mind. So we can say the steady state response analysis depends on the type of the control system, and which is the number of open loop holes which are going to occur at the origin. Whereas the transient state analysis depends on the order of the control system, which is the highest power of S in the characteristic equation. So simply what I can say, the steady state analysis is always going to depend upon the type of the control system, whereas the transient state analysis is always going to depend upon the order of the control system. So these things always you have to keep in your mind. So now let's go for the another analysis, which is expression for the error for a given input. So what is the expression for the error for a given input? So what is the expression of the error for a given input? Now we are going to discuss. So this is basically a block diagram. So this is a basic block diagram. You can say here there is a controller, here there is a controller, here there is a system. So we are going to connect in cascade. Here there is a sensor. The input is R of S and the output is C of S. So we are going to keep the sensor in order to sense the output and give as a feedback to the input. So this is a B of S. So there is a summary here, plus minus. So E of S is nothing but R of S minus E of S. And this P of S is nothing but controller gain into E of S. So this is we can say the basic block diagram of any control system. So this we can represent in a shortcut, which is this is a G of S. So I'm going to combine these two gains and I'm going to decide the G of S. Here for this the input is E of S and output is C of S. Input is G of S and output is C of S. So this is the overall gain is G of S. And the sensor gain is H of S. And this is the B of S and this is the C of S. And the input is R of S, it is the summer, plus minus. So now we can say what is E of S? E of S is equal to R of S minus B of S. So what is B of S? B of S is nothing but H of S into C of S. Same thing you have substitute. So B of S is nothing but H of S into C of S. Then what is C of S? C of S is equal to E of S into G of S. So C of S is equal to G of S into E of S. So now if you simplify, if you take this part to the left side and if you simplify, we are going to get E of S is equal to R of S by 1 plus G of S H of S. So this is the expression of the error for a given input of R. E of S is equal to R of S by 1 plus G of S H of S. Then what is the steady state error? Final value theorem, I've already told you. So final value theorem is steady state error is equal to limit S t tends to infinity, U of t is equal to limit S tends to 0 S into E of S. So this is the final value theorem. So now we can apply the final value theorem in order to get the steady state error between the input as well as the output. So this is the expression of the steady error, which is the E of S. E of S is the error, which is equal to R of S by 1 plus G of S H of S. So if you want to know what is the steady state error, E of S is equal to limit t tends to infinity, E of t is equal to limit S tends to 0 S into E of S. Time is infinity means S is 0. If time is 0 means S is infinity. So I have already told this important formulas. So this is the initial value theorem and the final value theorem. So if t is infinity means S is 0. As t is 0 means S is infinity. Both are vice versa, opposite in nature. So with the help of steady state error, with the help of this expression, you can get the steady state error between the input as well as the output. So this formula always you have to keep in your mind, which is E of S is equal to R of S by 1 plus G of S H of S. And steady state error is equal to limit t tends to infinity, E of t is equal to limit S tends to 0 S into E of S. So this is all about the steady state error. So this is the expression of the error for any given input in the terms of the Laplace domain. So now the next concept is the expression of the steady state error for a given input and the disturbance. So now I am going to figure out the expression of the steady state error for a given input as well as the disturbance also. So this is all about the expression of the steady state error for a given input as well as the disturbance. So you can see clearly this is the block diagram that we are going to represent. Here the input is R of S and output is C of S. So here there is a some transfer function g1 of s, and here there is a transfer function g2 of s. So this is a sensor transfer function which is h of s, and the output is b of s, and here it is a e of s. So between these two systems, we are going to keep another summer. Here it is going to provide some disturbance which is d of s. So it is going to provide some disturbance which is d of s. So now we need to find what is the expression of the steady state error for a given input as well as the disturbance also we want to require. Then what is E of s? So what is block diagram? Here R of s is the input and E of s is the disturbance in the Laplace domain. So E of s is equal to R of s minus B of s. Then what is B of s? B of s is equal to C of s into H of s. So B of s is nothing but C of s into H of s. Same thing. Then what is C of s? C of s is nothing but we can say C of s is nothing but E1 of s into G1 of s plus D of s overall G2 of s. So therefore here we can say C of s is nothing but E of s into G1 of s plus D of s into overall gain G2 of s. So this is all about the C of s, and remaining everything is same, which is H of s. So therefore now if you simplify, if you take this E of s to the left side and if you simplify, finally we are going to get the value of E of s which is equal to R of s minus T of s into G2 of s into H of s by 1 plus G1 of s into G2 of s into H of s. So this is all about the E of s that we are going to get, which is equal to R of s minus D of s into G2 of s into H of s by 1 plus G1 of s, G2 of s, H of s. So this is the overall expression of the steady state error with the help of input as well as the disturbance. So you can see clearly the R of s is the Laplace transform of input and E of s is the Laplace transform of the disturbance. So output is going to include both the input as well as the disturbance also. So if I am going to split into two parts, then I am going to get R of s by 1 plus G1 of s, G2 of s, H of s minus D of s into G2 of s into H of s by 1 plus G1 of s, G2 of s, H of s. So I have split this denominator into two parts. So this is the expression that I am going to get. So this is because of the input and this is because of the disturbance. Here R of s is there, so because this is the error because of input, and here D of s there means this is because of the disturbance. Then what is steady state error? You know, the steady state error is equal to limit t tends to infinity, E of t is equal to limit s tends to 0, s into E of s. Same thing we written. Steady state error is equal to limit t tends to infinity, E of t is equal to limit s tends to 0, s into E of s. Then what I am going to do? I am going to assume input is equal to 0. So I am going to assume input is equal to 0 and H of s is equal to 1 and D of s is equal to 1 by s. I am going to assume like this because I am going to assume that disturbance is nothing but U of t I am going to assume. So D of t is equal to U of t, so D of s is equal to 1 by s. So for analysis purpose I am going to assume like this. And also I am going to assume the input is equal to 0. I am going to assume this R of s is equal to 0. So I am also going to assume H of s is equal to 1. Then I have assumed the disturbance is equal to U of t, so D of s is equal to 1 by s. Then I will see by applying this one for this one what I am going to get. I will see now. So the steady state error ESS is equal to, when the input R of s is equal to 0, then what I am going to get, this part is 0. So this part is 0 means only this is there. And then H of s is what? Here also H of s is there. So we are going to get minus D of s into G2 of s by 1 plus G1 of s, G2 of s. So this is the E of s you are going to get. But we want steady state error means E of s is equal to limit s tends to 0, s into E of s. E of s value you know into multiply by s and keep the limit s tends to 0. So we can say s into minus D of s G2 of s by 1 plus G1 of s, G2 of s, limit s tends to 0. So if we simplify, we are going to get in this fashion, which is minus limit s tends to 0, s into D of s, G2 of s by 1 plus G1 of s, G2 of s. As I've already told you, we have assumed D of s is equal to 1 by s. Then what we are going to get? Here s and s are going to get cancelled. We are going to get finally the steady state error in the input R of s is equal to 0 is equal to minus limit s tends to 0, G2 of s by 1 plus G1 of s, G2 of s we are going to get. So now we can take this limit in the upper side as well as the in the downside also. We can keep this limit, which is limit s tends to 0, G2 of s we are going to get some value G2. So limit s tends to 0 with G2 of s is nothing but we are going to get some value which is equal to G2. And limit s tends to 0, G1 of s is nothing but we are going to get some value G1. And limit s tends to 0, we can say basically then g1 of s into g2 of s, then what is the value we are going to get? It is equal to g1, g2. So you can see clearly. So limit s tends to 0, g1 of s, we are going to get some value g1. Limit s tends to 0, g2 of s, we are going to get some value g2. Then limit s tends to 0, g1 of s, g2 of s, nothing but just a multiplication of these two values, the g1, g2. Substitute these values. So here we are going to get its value is equal to g2. Here we are going to get 1 plus g1, g2. So here actually there should be minus, but we are taking the magnitude part. So because of that, we are going to get only the positive values, which is equal to g2 by 1 plus g1, g2. So finally, actually what you will get here? Actually you will get here minus g2 by 1 plus g1, g2. You are going to get actually like this. But I am going to take the magnitude only. If I take the magnitude, this part is going to get out. Then I am going to get only the positive values. g2 by 1 plus g1, g2 I am going to get here. So you can see clearly here. As g1 increases, suppose if g1 increases, then what is going to happen? As g1 increases means the denominator part is going to get increased, so overall part is going to get decreased. So as g1 increases, then the amount of the steady state error will decrease. So therefore we can say as the g1 value increases, then the overall steady state error is going to get decreased. So what is g1? g1 is nothing but DC gain of this one, is limit s tends to g1 of s, limit s tends to g1 of s. So if this value is going to get increased, then what is going to happen? The overall the steady state error is going to get decreased. So therefore, whenever the limit s tends to 0, g1 of s, when its value is increasing, then the steady state error is going to get decreased. It is going to get decreased in this case. So as g1 increases, then the steady state error is going to get decreased. So this is the expression of the output with respect to input as well as disturbance. So we are assuming a special case of R of s is equal to 0 and H of s is equal to 1 and E of s is equal to 1 by s. So we got the expression like this, so steady error, and also we got the amount of steady state error. So we can say as the value of g1 increases, then the amount of the steady state error is going to get decreased. So all these things we can see from this expression. We are going to discuss another concept, which is the steady state error for the different types of inputs. So we are going to figure out the steady state error expressions for the different types of inputs. So we are going to figure out the steady state error for the different types of inputs. So this is the basic block diagram in the case of control system. Here it is G of s, here it is H of s, here it is R of s, here it is C of s, and it is E of s. So there is a feedback here. It's a negative feedback. By default, always we are going to study only the negative feedback. Then I've already told you what is E of s formula. E of s is equal to R of s by 1 plus G of s H of s. This one just now we have discussed. So therefore, E of s is equal to R of s by 1 plus G of s H of s. Then first step input. The step input means we can say the R of t is equal to A into U of t. The step input means R of t is equal to A into U of t. Then what is R of s, which is equal to A by s? So the Laplace transform of input is R of s is equal to A by s. So if you substitute here, then we can say in the place of R of s, if you substitute A by s, then you know the steady state error formula. Steady state error is equal to limit s tends to 0, s into E of s. So s into E of s. So you know E of s is equal to R of s by 1 plus G of s H of s. So s cancels, we are going to get finally A by 1 plus C of s H of s. That is the limit. So limit, if you take it downward, then we are going to get A by 1 plus limit s tends to 0, G of s H of s. So I am going to assume this is limit s tends to 0, G of s H of s. I am going to assume its value is equal to Kp. So therefore finally you are going to get the steady state error is equal to A by 1 plus Kp. So this is the expression of the steady state error that we are going to, which is Vs is equal to A by 1 plus AB, where Kp is equal to limit s tends to 0, G of s into H of s. So Kp is equal to proportional constant. So this is the expression of the steady state error for a step input. Now for ramp input, means R of t is equal to At into U of t. This is the general expression. So ramp input means R of t is equal to At into U of t. Then we can say R of s. The Laplace transform of input R of s is equal to A by S square, because you know the Laplace transform of t to the power of n is equal to L factorial by s to the power of n plus 1. So by using that formula, we are going to get the Laplace transform of R of s is equal to A by S square. So you know what is the steady state error formula? So you know the steady state error is equal to we can say limit s to is equal to limit s tends to 0, s into E of s. But E of s, you know, is equal to R of s by 1 plus G of H of s, and R of s value is equal to A by S square. So A by S square by 1 plus G of s H of s. So G of S, H of S. So if you simplify, here S square, here S. So S is cancelled, we are going to get S. If we take this S down, we are going to get S plus S into G of H of S. So if we substitute S is equal to 0, then this part is equal to 0. So only this part is going to remember, which is A by kV. kV is nothing but limit S tends to 0, S into G of S, H of S. So this is the value of the steady state error, which is equal to A by kV, where kV is equal to limit S tends to 0, S into G of S, H of S. So this you are going to get from this expression. So this is the expression of the size error for the ramp input. Now for the parabolic input, for a parabolic input, this R of t is equal to A by 2 into t square into U of t. So this is the parabolic input. R of t is equal to A by 2 into t square into U of t. So this is the parabolic input, which is R of t is equal to S square by we can say A by 2 into t square into U of t. So this is the standard format. Always you have to remember, which is R of t is equal to A by 2 into t square into U of t. So then what is the Laplace transform of the input? R of is equal to A by S cube, that we are going to get here. Then the size of the formula. So we just now we have discussed size of is equal to limit S tends to 0, S into we can say E of S. E of S is nothing but R of S by 1 plus G of H of S. R of S which is A by S cube. Then 1 plus G of S, H of S. So here S here S cube plus S cube we are going to get. If you take S square downward, you are going to get S square plus S cube G of H of S. If you substitute S tends to 0, then if this part is 0, then here you are going to get S square into G of H of S. So this part I am going to assume its value is equal to Ka. So Ka is equal to limit S tends to 0, S square into G of H of S. So finally the size area is equal to A by Ka. So this is the formula you have to remember. So finally you have to remember like this. For a step input R of t is equal to A into U of t, the steady state error is equal to A by 1 plus Kp, where Kp is equal to limit S tends to 0, G of H of S. For the ramp input R of t is equal to AT into U of t, the size error is equal to A by Kv, where Kv is equal to limit S tends to 0, S into G of H of S. And for parabolic input R of t is equal to A by 2 into t square into U of t, then the size error is equal to A by Ka, where Ka is equal to limit S tends to 0, S square into G of H of S. All these formulas always you have to keep in your mind. So therefore, finally I can say, for a step input R of t is equal to A into U of t, the size error is equal to A by 1 plus Kp, where Kp is equal to limit S tends to 0, G of H of S. And for ramp input R of t is equal to AT into U of t, the steady state error is equal to A by Kv, where Kv is equal to limit S tends to 0, S into G of H of S. And for parabolic input R of t is equal to A by 2 into t square into U of t, the steady state error is equal to A by Ka, where Ka is equal to limit S tends to 0, S square into G of H of S. Where Kb is equal to proportional constant, Kv is equal to the velocity constant, and Ka is equal to the acceleration constant. Listen carefully. Kb is equal to proportional error constant, and Kv is equal to the velocity error constant, and Ka is equal to the acceleration error constant. All these things always you have to keep in your mind. So this is all about this concept. So the next one is generally we are going to represent the open loop transfer function, which is G of H of S in this format, which is the general way of representation of the open loop transfer function, which is G of H of S is equal to K into 1 plus the S goes on by S the power of T into 1 plus T1S goes on. So this is the standard representation of the open loop transfer function. So now I am going to give you this table. This table is a very, very important table. So if you remember this table, you can solve this question in a fraction of seconds. So this is the type of the system, and this is the steady state error for different types of inputs, for step input, for ramp input, and for parabolic input. So this is the type of the system, and this is for the steady state error for the step input, ramp input, and parabolic input. So type 0, type 1, type 2, step input, ramp input, and parabolic input. So always remember like this, which is A by 1 plus Kb, here A by Kv, here A by Ka, and these downwards are always zeros, and these upper parts are always infinity. So this part always you have to keep in your mind. So the type of the system, here it is inputs, type 0, type 1, type 2, here it is a step input, ramp input, and parabolic input. Here it is A by 1 plus Kp, here A by Kv, here A by Ka, the downwards are always 0, and the upper parts are always infinity. So if you remember this we can say for type 0 system, for step input we have find error Whereas for ramp input and parabolic input, we have infinite error. Whereas for type 1 system, for step input, we have zero error. For ramp input, we have find error. But for the parabolic input, we have infinite steady-state error. Whereas for the type 2 system, for step input, we have zero steady-state error. For ramp input, we have zero steady-state error. Whereas for parabolic input, we have finite steady-state error. So these things always you have to keep in your mind. So if you remember this table, we can solve these questions in a very fraction of seconds. So let me write these parts somewhat clear so that we can easily able to view it. So this is basically step input. So this is basically step input. So this is a step input and this is the ramp input. So this is the ramp input and this is the parabolic input. So this is the parabolic input. So these things always you have to keep in your mind. So these things always you have to keep in your mind here. So this is step input, ramp input and parabolic input. So now I think you are able to see it very clearly. I already told you what's the type of a system. Type of a system is for the in the open loop transfer function, the number of poles which are going to present at the origin is called as the type of the system. So this P is called type of the system. If P is equal to 0, we say it's a type 0 system. If P is equal to 1, we say it's a type 1 system. And if P is equal to 2, we say it is a type 2 system. If P is equal to n, we say it is a type n system. So now we'll discuss some more important points here. We can apply all formulas only after checking that the given system is perfectly stable. So basically, we can apply all these formulas only after confirming that the given system is a stable system. So if you have confirmed that the given system is a stable system, then only you have to apply these formulas. Otherwise, you don't have to apply, because if it's an unstable system, then definitely the surge error is always equal to infinity. So before you apply this formula, first you have to confirm whether the given system is stable or not. If it is stable, then only you have to apply this formula in order to get the steady-state error. If it is unstable, means by default we can say the steady-state error is equal to infinity. So we can apply all formulas only after checking that the given system is perfectly stable. Means we can say if the given system, so first you have to check whether the given system is stable or not. If it is stable, means then only we can say it will have some finite error. Otherwise, it will always have an infinite error. If the given system is unstable, then always the steady-state error is always equal to infinity. So therefore we can say if the given system is unstable, then we can definitely say the given system is will have a steady-state error of infinity. If any term missing in characteristic equation, then the system is perfectly unstable. This one also I already told you. In the characteristic equation, if any power of the term, if it is missing, then definitely we can say the system is said to be perfectly unstable. Then definitely we can say the steady-state error is always equal to infinity. So these things always you have to keep in your mind. So therefore we can say finally, so before you apply all these formulas, first you have to check whether the given system is stable or unstable. If it is stable, then only we have to apply these formulas. Otherwise, we don't have to apply this. For unstable system, always the steady-state error is always equal to infinity. So suppose in the characteristic equation, if any term is missing, means by default we can say the system is said to be unstable. So how to check whether the system is stable or unstable? Just by seeing doing a Raoult-Sarras criteria for the characteristic equation. If any poles which are going to line axis of S plane, we say it is an unstable system. If all the poles are going to line axis of S plane, we say it is a stable system. So just by doing the RH criteria, then we can confirm that the given system is stable or unstable. If it is stable, then only we have to apply this formulas. Otherwise, if it is an unstable system, is always the steady-state error is always equal to infinity. So these things always you have to keep in your mind. So now the next concept is the error series. So basically in the previous concept we have learned about the steady-state error, means only at the final value we are going to get the error, but not at each and every time. So at each and every time, what is the error? We don't know the expression. So what is the error at each and every time? We don't know. With the help of the previous concept, means we can only get the error only at the steady state, but not at each and every any other instant. So if you want to get the what is the value of the error at each and every time, then this is the concept. So error series means with the help of this concept, now we will get back. Now we will know what is the error at each and every time. So E of S is equal to R of S by 1 plus G of S H of S. So I am going to assume let F of S is equal to 1 by 1 plus G of H of S. So this is what I am going to assume, which is F of S is equal to 1 by G of S H of S. So therefore E of S is equal to R of S into F of S. Then I am going to apply the Laplace inverse on the both sides. So Laplace inverse of f is equal to Laplace inverse of r of s into f of s. So I already told you, conversion time domain will give you product in the Laplace domain. So I already told you, convolution in the time domain will give you the product in the Laplace domain. So therefore, E of t is equal to r of t convolution of f of t. So therefore, I have already told you that convolution time domain will give you the product in the S domain, Laplace domain. So E of t is equal to r of t convolution of f of t. So if you apply the convolution property, we are going to get tau is equal to, basically we can say tau is equal to minus mu to plus t f of tau into r of t minus tau. So we can apply the r of t convolution of f of t or f of t convolution of r of t, anything which is same. Here we are going to use the f of t convolution of r of t. So therefore we can say f of tau r of t minus tau d tau. Here basically tau is equal to minus infinity to plus infinity, but we will take only from tau is equal to 0 to plus infinity only we are going to confirm. Only from tau is equal to 0 to plus infinity means below this one we have to assume the input is not given. So it's basically input is given from only tau is equal to 0 but not below that one. So based on this we can say tau is equal to 0 to tau is equal to plus infinity. So this is what we have to assume, because r of t minus tau means we can say the input r of t basically it is present only from it is only present from t is equal to 0 onwards, above only, but not below. So based on this property we are going to apply tau is equal to 0 to plus infinity. Then what is r of t minus tau? So we know with the help of the Taylor series, r of t minus tau which is equal to r of t minus tau into r dash of t plus tau square by 2 into r double dash of t minus tau cube by 3 factorial into r double dash of t and goes on. So listen carefully, r of t minus tau which is equal to r of t minus tau into r we can say basically r derivative of the r of t plus tau square by 2 into r double dash of t minus tau cube by 3 factorial into r triple dash of t is derivative. One dot means first derivative, double dot means second derivative, triple dot means three derivative, and it goes up. Plus minus plus minus plus minus. So this is the r of t minus tau is equal to r of t minus tau into r dash of t plus tau square by 2 into r double dash of t minus tau cube by 3 factorial r triple dash of t plus tau to the power of 4 by 4 factorial r 4 dash of t and goes on. So now you know E of t is nothing but, so you know E of t is equal to f of tau into r of t minus tau. So r of t minus tau you know, r of t minus tau you know. So this is the expression. Just substitute here. Then what is the thing that we are going to get? If you multiply these two things, f of tau and this one, so if you see r of t is a constant, because we are doing integration from with respect to tau. So t is a constant, so we can take it outside integration. Then finally we are going to get is equal to r of t integration from tau is equal to 0 to infinity f of tau into d tau minus r dot of t integration from tau is equal to 0 to infinity tau into f of tau d tau plus 2 we can say r double dash of t by 2 factorial integration from tau is equal to 0 to infinity tau square into f of tau d tau. Because I've already told you here basically t is a constant, so definitely r of t, r dash of t, r double dash of t, everything is a constant. We can take it outside the integration, and like 2 factorial, 3 factorial also constant, we can take it outside the integration, and the remaining parts we have to integrate. So basically we have multiplied f of tau and r of t minus tau, and r of t, r double dash of t, all this is a constant. We have taken outside the integration. So this is the equation that we are going to get finally. So now what I am going to do, I am going to assume this value is nothing but k naught. So this value I am going to assume k naught. So k naught into r of t plus. So this value I am going to assume it is nothing but k1 by 1 factorial. So I am going to assume this value is nothing but k1 by 1 factorial. So k1 by 1 factorial, here it is a r dash of t plus. So this I am going to assume. So basically here this value, see basically this value I am going to assume it is equal to k1. So k1 I can write like by 1 factorial into r dash of t plus. Here this is nothing but basically this I am going to assume it is equal to k2. So this is basically I can assume this is k2. So k2 by 2 factorial into r double dash of t plus same thing k3 by 3 factorial r double dash of t and goes on. So like this we are going to get. So if you see clearly here there is a 1 factorial. So basically you can write like this 1 factorial. So that is the reason Here we have taken like this one. So this value we have assumed it as is k0. This with minus we have taken this value as a k1, and with plus we have assumed this value as a k2 and goes on. So finally we are going to get E of t is equal to k0 into r of t plus k1 by 1 factorial into r dash of t plus k2 by 2 factorial r double dash of t plus k3 by 3 factorial r triple dash of t and goes on. So now if you see clearly, we got the expression of the error with respect to input in the time domain. So this is the relation between the error and the input in the time domain, which is E of t is equal to k1 into r of t plus k1 by 1 factorial r dash of t plus k2 by 2 factorial r double dash of t plus k3 by 3 factorial r triple dash of t and goes on. So what is the such error? Such error is equal to limit t tends to infinity E of t in the time domain. Then what is k0? K0 is nothing but integration from 2 is equal to 0 to infinity f of tau d tau. So now this is nothing but, basically we can say, so this is nothing but simply we can say limit s tends to 0 f of s. So this is called as a f of s. So basically, so listen carefully. So for f of t, the Laplace transform of f of t is nothing but f of s is equal to integration from we can say at t is equal to 0 to infinity f of t e to the power of minus st into dt. So if you substitute s is equal to 0, then what you are going to get? Limit s tends to 0 f of s. So you are going to get integration from t is equal to 0 to infinity f of t into dt. So replace t by tau, then you are going to get this expression. So this value is nothing but limit s tends to 0 f of s. Similarly, what is the k1? So k1 is nothing but this value with negative. So minus of integration from tau is equal to 0 to infinity 2 into f of tau d tau. Same thing, k1 is equal to minus of integration from tau is equal to 0 to infinity 2 into f of tau into d tau. So this value is nothing but which is equal to limit s tends to 0 df of s by ds. Same thing, if you do the derivative of the df of s by ds, we are going to get some value, and if you substitute s is equal to 0, then we are going to get like this, which is equal to minus integration of tau is equal to 0 to infinity 2 into f of tau into d tau. Similarly, what is k2? K2 is nothing but it is equal to, we can say this plus integration from tau is equal to 0 to infinity tau square into f of tau d tau. So this is a k2. So this is nothing but limit s tends to 0 d square f of s by ds square. So this is the expression that we are going to get. So do the two terms of derivative and finally substitute s is equal to 0. So we are going to get the value of k2. So this is a k0, this is a k1, and this is a k2. So like this and goes on. So goes on. Similarly, k3 is again minus integration from tau is equal to 0 to infinity tau cube into f of tau d tau is equal to limit s tends to 0 d cube f of s by ds cube. Same thing. So listen carefully, plus minus, same thing like this. Finally, so kn is nothing but integration from tau is equal to 0 to infinity minus tau all the power of n f of tau d tau is nothing but limit s tends to 0 d to the power of n f of s by ds to the power of n. So this is the general expression that we are going to get. So if you substitute k is equal to 0, we are going to get the first one. If substitute k is equal to n is equal to 1, we are going to get the second one like that. So this is the general expression of the kn. So this is a thing always you have to keep in your mind. So now the relation between a static and the dynamic error constants. So this is all about this one. So the exact expression of the sized error and the input with respect to time, and you also know the value of k0, you know the value of k1, you know the value of k2, and you also know the value of k3. Everything you have know. So f of s is nothing but 1 by g of s, 1 by 1 plus g of s, h of s. So you can get the value of the error at any time with respect to input at any time. So this is a relation, the time domain expression. So this is all about this one. So what is k0? K0 is equal to limit s tends to 0 f of s d of s. K1 is equal to limit s tends to 0 d into f of s by ds, and k2 is equal to limit s tends to 0 d square f of s by ds square, and finally kn is nothing but limit s tends to 0 this another derivative of f of s with respect to s. So this is the relation that you always have to keep in your mind. So now the relation between the static and the dynamic error constants. So previous concept is called static error constants, and this one is called as the dynamic error constants. So the previous concept are called as the static error constants, and this is called as the dynamic error constants. So what is k0? K0 is nothing but limit s tends to 0 f of s. So what is f of s? So limit s tends to 0. What is f of s? 1 by 1 plus g of h of s. So if we take the limit, then we are going to get 1 by 1 plus limit s tends to 0 g of h of s. So limit s tends to 0, g of h of s is nothing but kp. So therefore, this value is equal to kp. So therefore, k naught is equal to 1 by 1 plus kp. So this is the relation between the static error constant as well as dynamic error constant. K naught is the dynamic error constant and kp is the static error constant. Similarly, in the same fashion, so k1. So what is k1? K1 is nothing but So k1 is nothing but limit s tends to 0 d into f of s by ds. So if we simplify, we are going to get k1 is equal to 1 by kv and k2 is equal to 1 by ka. So this is the relation between the static error constant as well as dynamic error constant, which is equal to k0 is equal to 1 by 1 plus kp and k1 is equal to 1 by kv and k2 is equal to 1 by ka. So these things always you have to keep in your mind. So this is the basic relation between the static error constants as well as the dynamic error constants. So we can say k0 is equal to 1 by 1 plus kp and k1 is equal to 1 by kv and k2 is equal to 1 by ka. So this is the basic relation between the static error constants as well as the dynamic error constants. So these things always you have to keep in your mind. So this is the basic relation between the static error constants as well as the dynamic error constants. So k0 is equal to 1 by 1 plus kp and k1 is equal to 1 by kv and k2 is equal to 1 by ka. So finally, we have to remember which is p of t is equal to k0 into r of t plus k1 by 1 factorial r dash of t plus k2 by 2 factorial r double dash of t plus k3 by 3 factorial r triple dash of t and goes on. And what is the kn? Kn is equal to limit s tends to 0 and the derivative of f of s with respect to s, and f of s is equal to 1 by 1 plus g of h of s. So if you remember this one, everything is clear. So remember, e of t is equal to k0 into r of t plus k1 by 1 factorial r dash of t plus k2 by 2 factorial r double dash of t plus k3 by 3 factorial r triple dash of t and goes on. And kn is equal to limit s tends to 0 and the derivative of f of s with respect to s. We can substitute the value of n from 0, 1, 2, 3 and goes on. And f of s is equal to 1 by 1 plus g of s h of s. So if you remember these formulas, everything is simple and clear and cut. So this is all about this concept. Now we are going to discuss another concept which is called as the potentiometer. So this is the concept regarding the potentiometer. So you can see clearly in this picture. So there is a we can say this is the input and this is the output. So this is the input voltage is EI and the output voltage is E naught. So this is the, we can say xt. This is the total distance is xt and xi is the so basically here we have taken small amount of displacement. So xi is called as the input displacement of the wiper. So this is the input displacement of the wiper, and E naught is the output voltage, and xt is the total length of the resistance, and rp is the total resistance of the part, and we can say rp by xt is called the resistance per the unit length, and kp is called as the pot gain. So these are the, we have to remember these are the formulas. So we can say ei. So basically we can say xi. This xi is called as the input displacement of the wiper. First, this is the wiper. We are going to displace this one either upward or downward in order to get the voltage E naught. So xi is called as the input displacement of the wiper, and E naught is called as the output voltage, and xt is the total length of the resistance, and rp is the total resistance of the pot. So therefore, if rp is the resistance, if rp is the total pot resistance in the length of xt, then what is rp by xt? Rp by xt is the resistance per unit length. The resistance per unit length. So rp by xt is the resistance per unit length, and kp is called as the pot gain. Then with the help of voltage division principle, we can say E naught is equal to this resistance by total resistance. So what is the unit length resistance? Rp by xt, and this length is xi. So therefore Rp by xt into xi, this is called as a this much amount of resistance is present here. By total resistance is Rp into input voltage is Ei. So Rp cancels, we are going to get E naught is equal to xi by xt into Ei. So xi by xt is nothing but we are going to call this as the pot gain, which is xi by xt is called as the pot gain. Its value is always less than or equal to 1 because xi is always less than or equal to xt. So therefore we can say its value is always less than or equal to 1. So therefore we can say this is the equation that we are going to get. E naught is equal to kp into xi. So the output voltage is equal to kp times the input displacement. So E naught is equal to Kp. Kp is nothing but constant. So you can see clearly A is a constant, input voltage is constant, and Xt is also constant. The only variable is Xi. So Xi is the variable. So therefore Kp into Xi, because A is a constant, Xt is a constant. Sorry, basically here Kp is nothing but it is the ratio of Ei by Xt. Small correction here. Kp is the ratio of Ei by Xt. Ei by Xt. So this value, it is not less than or equal to 1. Actually, we don't know its value. So therefore, we have to arrange this one. Small correction here. So this point always you have to keep in your mind. So here Kp is nothing but pot gain. It is a ratio of the Ei by Xt. Ei by Xt. So Ei by Xt is nothing but pot gain into Xi. So Xi is the input displacement of the wiper and E naught is the output voltage. So this is the relation. E naught is equal to Kp into Xi. So this is the time domain. So if you apply Laplace transform, we are going to get E naught of S is equal to Kp into Xi of S. So this is the relation between the output voltage and the input displacement, which is E naught of S is equal to Kp into Xi of S. So this is the relation between the output voltage as well as the input displacement, which is E naught of S is equal to Kp into Xi of S. So therefore, if you want to draw the block diagram, we are going to get here the gain factor is Kp and the input is Xi of S and the output is E naught of S. So this is the we are going to say this is the transfer function of the block diagram of the potentiometer. Here the input is basically it is the displacement and output we are going to get the voltage. So therefore E naught of S is equal to Kp into Xi of S. E naught of S is equal to Xi Kp into Xi of S, where Kp is the pot gain and E naught of S is the output voltage and Xi of S is the input displacement. So E naught of S is equal to Kp into Xi of S. So E naught of S is equal to Kp into Xi of S. So E naught of S is equal to Kp into Xi of S. E naught is the output voltage and Kp is the pot gain. Kp is nothing but it is a ratio of the Ei by Xt. And Xi of S is nothing but it is a input displacement of the wiper. So this is the, you can say, the concept regarding the potentiometer. So therefore, E naught of S by Xi of S is equal to Kp. So this is all about the potentiometer. Let's go for the tachometer. So this is the another concept which is about the tachometer. So you can see clearly this is a diagram of the tachometer. So you can see clearly this is a reference. So this is the reference winding and this is the control winding. So this is a reference winding and this is a control winding. So this is a constant voltage that we are going to give across this reference winding. Here is the reference voltage and this is a constant voltage that we are going to get applied. So this is a rotor. So this is a load here. So as the load is going to get rotate, with some speed omega and angle displacement theta and angle velocity omega. So because of this rotation, some type of voltage is going to get induced in this winding. This is called the control voltage. So control winding, in this some voltage is going to get induced, is called E naught. So now you can see E naught is always directly proportional to the speed it is going to get rotate. So basically with the help of tachometer, we have to measure what is the speed of the rotation of this shaft I want to figure out. So if you keep, because of this rotation, because of this rotation, some voltage is going to get induced. So E naught is directly proportional to omega. So if you remove proportional to the constant, we can say E naught is equal to Kt into omega. So this is the, if you want to remove the proportional to the constant, you have to keep a constant, the value is equal to Kt. So if you apply the Laplace transform, then we are going to get E naught of S is equal to Kt into omega of S. So E naught of S is equal to Kt into omega of S. So if you want to draw the block diagram, the output is E naught of S and the input is omega of S. Then we are going to get E naught of S is equal to Kt into omega of S. Because the output is the voltage and the input is the angular velocity. Whereas Kd is called tachometer gain. Kd is called tachometer gain. So basically, E naught is directly proportional to omega is rate of change of angular displacement, which is beta by dt. So if you want to remove proportional to constant, use a constant, is called Kt. So E naught is equal to Kt into beta by dt. So if you apply Laplace transform, we are going to get E naught of S equal to S into Kt in beta of S. Then if you want to basically draw the block diagram, then the output is E naught of S, gain is Kt into S, and the input is theta of S. So these are the two different ways of writing this one, which is the same figure. So you know omega is equal to d theta by dt. So if you apply the Laplace transform, you are going to get omega of s is equal to s into theta of s. So you can write even in this fashion also. Still we are going to get the same result. So if we replace omega s by s and theta of s, so keep s inside, then we are going to get this is a logarithm that we are going to get. So here the input is the we can say input is the velocity, angular velocity, and output is the voltage. So therefore, E naught of s is equal to kt into omega of s, or E naught of s is equal to s into kt into theta of s. So these things always you have to keep in mind. So therefore, we can say for this tachometer, the input is the angular velocity and the output is the voltage. So for this tachometer, the input is the angular velocity and the output is the voltage. So these things always you have to keep in mind. So always remember for the potentiometer, E naught of s is equal to kp into xi of s, and for the tachometer, E naught of s is equal to kt into omega of s. So these things always you have to keep in your mind. Here the input is the angular velocity and the output is the voltage. So this is all about this tachometer.